So start, my friend. Yes.
Okay. Good morning,
Diego,
everyone.
can you? Well, you are recording everything. No? Hi, Vicente. How are you?
Hello. I'm good, and you?
Yeah. Very well, thank you.
The video streaming is already up.
Yes.
Okay.
And also the video streaming is recording for us.
So we are.
So okay, let's get
Yeah.
let it go.
Let's go. Yes.
Okay.
Well, good morning to everyone. As Research Director of the Electrical Engineering Department of the University of Santiago de Chile, and in collaboration with colleagues from Toledo, Brazil, who have helped us to prepare the conference in this new version, I give you the warmest welcome to the third South American Colloquium on Visible Light Communications 2021. This opportunity is an online version due to the pandemic situation around the globe. Well, first of all, I would like to thank Professor Sacvlc for his great support in helping us from the first version of the conference. He's the head of Optical Communications Research Group in Northumbria University, England. He has guided and helped us with patience and wise advice in order to succeed with the conference. I would also like to thank all the professors who have kindly agreed to act as keynote speakers in this new version of the conference. Professors Ashgar Golami, Ana Maria Begni, Rui Wang, Luis Nero, Ali Kaliji, and Cesar Azurdia Mesa. Thank you very much. I also thank all professors of the steering and local organizing committees, to the industry people who are interested in participating in this event, and to all the students who are in one way or another being part of this event, as authors and co-authors in different papers. I hope that you all enjoy and participate actively in the conference while discussing new ideas and hopefully generating new types of collaboration. I wish you all a great event. Enjoy, have fun. Thank you very much.
Okay. Professor Edson, do you want to say a few words to start?
Alexander, yes. Yes.
So, hi everyone. Hello. Good morning, everyone. Good morning, everybody. It's a pleasure and an honor to be here at the opening of the third South American Colloquium on Visible Light Communications. On behalf of the Federal Technological University of Paraná, Toledo campus, I would like to welcome everyone and hope that we have an excellent event. I would also like to thank all the support given by my friends at University of Santiago, Chile. Unfortunately, the COVID-19 pandemic did not allow us to welcome everyone here in Toledo, Brazil. But even so, we will have an excellent event, and we hope that in the future to have the event held here in Brazilian lands again.
Thank you, Professor Edson. Professor Fari?
Hi, good. Well, it's a very early morning for you guys, isn't it? I don't know, is it 7 o'clock or 6 o'clock?
Yeah.
Anyway, I just wanted to hello to everyone and welcome to this wonderful event. And this, as you know, this event started many years ago via my discussion that myself and Ishmael and a couple of other colleagues we had in Chile. And we knew at that time this is the beginning of a very interesting adventure, scientific adventure. And I always, as a individual, had a trust and belief that my colleague in Santiago will take this event further in years to come. And there we are into 2021, and we are seeing this event, which is growing. So therefore, it is so great to see the contributions across the board to this event, and also to see so many colleagues are basically brought together in order to celebrate the contribution of light right from the beginning of the Big Bang all the way to 2021. And I think that in my personal view is that South America and Central America has got a great opportunity to play really significant roles in shaping the future research direction in visible light communication or visible light with infrared communication. And therefore, I think we will, as a community in Europe, we will support this event as much as possible. And I'm sure that this event will go from strength to strength. So I like to basically say a warm welcome to every one of you. My special thanks to my good friend Ishmael and his team and all the local organizing committee for putting a lot of effort, putting this programs together. And of course, our international technical committee, which are been superb in order to assist and advise when necessary. And our speakers that they, as soon as we invited them, they immediately said, yes, we didn't have any situation where people would say, well, let me think about it and so on. And that just demonstrates that the commitment of colleagues towards this event in South America. And I also like to, say thank you to all the authors that they submitted and their paper have been did. Wish that all of us will enjoy this event, which I'm sure we will. I hope that everything goes well since this is online, and hopefully next year this will be in person, that we can travel to South America and be in close contact and have even more exciting discussion. Thank you very much for organizing the event, and I hope that everything goes well. Thank you.
Farid, do you want to say something about the Professor Farid?
Yes, if you allow me to share the screen.
Yes, please.
Can I share the
Yes,
screen?
yes, please.
And as you know,
yeah, you can share. Yes.
can you see it? And it just a week ago, we heard the sad news of one of our very close friend and a colleague, Professor Wallace, who passed away due to some long illnesses. And Tony was a very dear friend to me and many others. I know Tony since 1990s. And in fact, Tony was one of the pioneers in the field of infrared communications. And Tony and myself, we organized the first colloquium in 1991 in IET, in Faraday's lecture theater. And this was about optical wireless communication. We couldn't imagine that where it would lead to. And we had the speakers at that time from Berkeley, Cannes, and others. We invited them. And this was the first time we are exposing UK to this event. And Tony was a driving force in that, because Tony had a lot of involvement with IRDA, and he used to work at Hewlett-Packard and so on. So his contribution towards this field is really been magnificent. And as you can see that Tony came to the UK at a very young age, 18 years old or so, and he studied here at Newcastle University. He did his first degree just across the road from my institution, then moved on to Imperial College to finish the masters and PhDs and so on. And he did absolutely superbly, and and he's also the fellow of IEEE, fellow of Royal Society of Art, fellow of IE or IET. So Tony was a fantastic guy, and I believe that he was loved by everyone. We continue to work together up until now. We still have a joint supervision of PhD. In fact, Tony's PhD student have a paper here, and she's going to present it later on. So we will miss him, but we will need to celebrate his life. And the fact that we are mentioning it here, I think that just demonstrates that we are committed towards keeping Tony's memories alive. And just fun, I think, is that we have agreed in another conference that there will be a prize under Tony's name for papers from early career researcher in CSNDSP, and that will be every 2 years that we will give the prize under his name. So we want to basically keep the memory alive. In my view, that Tony is gone for a long holiday or somewhere, and hope that one day we will meet again. Thank you very much.
Welcome, Farid. Thank you very much.
Farid.
Diego, take control.
Yes, thank you. Well, Professor Ismail, do you want to say the last word, or we can start?
Let's go.
Let's go?
Let's
Okay.
go. Yes, yes.
Okay, good. So now we take control as a chair, Professor Alexander Paul, as a co-chair, Vicente Matus.
Okay. Are you listening to me?
Yes.
Yes.
Okay, Diego. Yeah, thank you very much. First of all, I would like also to thank the organizers and the colleagues of the University of Santiago. It was a very nice opportunity indeed to meet you all, even if it's just remote. As have been said before, we hope that in the next colloquiums we could meet personally. And I'd like to thank in name of our university to be part of the organization and also to contribute to this field of research. So once this is said, so I would like to say a few words. Let me see if Professor Golami is present here first.
Professor Golami is joining.
Yes, joining now.
Yeah, it seems he has connection problem.
Okay, Professor Golami. Okay, I think I see him. So let me introduce Professor Golami. Is our first speaker in this beginning of the colloquium. Professor Golami is born in Iran in 1970. He received the bachelor and the master degree in electrical engineering from Isfahan University of Technology in Iran in 1993 and 1996, and the PhD degree in gigabit Ethernet optical communications from the Sacvlc, École Supérieure d'Électricité in France in 2007. And from 1996 to 2002, he was working on RD lab in Iran. And after a postdoc fellowship at the École Supérieure d'Électricité, he has been working in Draka communications in the fiber product technology. No? And Professor Isfahan Askar Gholami is now in Iran at the Isfahan University of Technology. Professor Gholami, you are welcome to this colloquium. So if you want to say a few words before we play the video with your presentation. Or should we go ahead and yes, yeah.
Hi everyone.
Hi.
You hear me?
Yes.
Thank you so much for preparing this event, and I don't any other things to say. Thank you so much.
Okay. So we are then, Diego, able to run the video, and so after the video, yes.
Yeah, it's gonna be me, Professor.
Okay. Sorry, Vicente. Sorry.
Should I go on?
Yes.
Okay.
Good morning. My name is Sacvlc, an associate professor at Isfahan University of Technology, situated in the Isfahan, in the middle of Iran. And I would like to give my speech to you in the subject of optical camera communication. As the outline, I will introduce the OCC systems, and then the challenges of this system will be described, and afterward the application of this system will be described, and finally I will conclude my talk. As an introduction, the OCC systems is a practical version of VLC systems as a part of the optical wireless communication systems. OCC use a camera receiver instead of photodiode. And you know that cameras nowadays are available everywhere in the roadsides, in the vehicles, in smart devices, and also in the smartphones. And in the other hand, LEDs also exist as the transmitter of this system everywhere, and you can find them in the roads, in the buildings, and also in vehicles, smart devices. So implementation of this system will be very easy. And so this system is a low-cost system and is an attractive system or technology to be used in many applications. As a principal operation of this system, it consists of a transmitter in one side of the channel and a receiver in the other side of the channel. In the transmitter, light sources is modulated by the modulator using bit streams to modulate the light source intensity and color. And the light could be captured in the other side of the channel by the lens to perform an image on the image sensor. In the image sensor, the location of the light sources is separated, and so we could easily separate the signals without any interference. So the interference is not a big problem here, and we can use parallel communication easily. There is defined a standard as a part of the VLC systems for image sensor communications, and this system is mostly used for visible light communication, and also infrared could be used as the spectrum. And there are many different modulation schemes, and data rates is not more than some megabit per second. The distance is mostly for lower than 100 meters. Also, the receiver is the transmitter is LED and is screen. But there is some challenges as the low data rate and non-line of sight problem. As a challenges, low data rates is a challenge for this system. For example, the commercial cameras have a frame rate not more than 30 or 60 frames per second, which just limits the maximum symbol rate lower than 15 symbol per second or 30 symbol per second. And to increase the data rates, we have a lot of solutions. One of them is using parallel communication or MIMO systems, or using advanced modulation schemes, or using rolling shutter cameras, and or using special high-speed cameras. And we should consider that there are a lot of applications that don't need a lot of data rates. So this system with the commercial camera could be used for many applications. To increase the data rates, I will try to pass through slides rapidly. Increasing data rates in OCC can be used by using parallel communication. There is some challenges also. Also, we can use some modulation schemes as the PAM or parse amplitude modulation, or orthogonal frequency division multiplexing, or color shift keying. These are the modulation which permit us to have high data rates. This is the CSK or color shift keying, which use different LEDs in different color to send the symbols as the different colors, and also using screens to transmit the data with a lot of cells, and also using rolling shutter method or technology to increase the data rates. And there are some special camera with very high frame per second, up to 1 million frame per second, which can use also to increase the data rates. And here is a table which shows the effective data rate of some projects, some research works, and you can see one of them is up to 55 megabit per second, which is use a special image sensor called OCI. Frame rate variation is another challenge for the OCC systems, which the frame rate is unstable in the time for the most of the commercial camera and smartphone camera. It causes a sampling time error, and fortunately for the developed 4K smartphone and new smartphone, this problem is fixed. And here you can see the variation of the frame rates for different brand and models of the smartphones. The other problem or challenge for the OCC systems is non-line of sight problem. Non-line of sight problem is common for all of the optical wireless communication systems, and for OCC systems also exist. There are some solutions to reduce this problem, as using the light scattered or reflected from the walls ceiling to overcome this problem. And or in the outdoor applications, the light which is scattered from the air could be used to reduce this problem. For the practical implementation of this system, there are some challenges that I have listed here. Maybe the most important one is the mobility. When the camera or the transmitter wants to move, they will have to track the camera or the transmitter, and this is a challenge. And we need high-speed cameras. Interference of background noise, background lights, as the solar and lamps reflection to the camera can cause the problem. Full duplex links, especially for smartphones, because the smartphones don't have LED in all of their sides, and this limits the transmission of data from the smartphone. The nonlinearity behavior of LEDs and display devices that limits the using of the sophisticated modulation schemes, and also the blurring and interpixel interference effect also limits the application of OCC, and the low-cost, high frame rate cameras, another challenge for these systems. Okay. We want to go to the applications to describe some applications for this system. Maybe one of the important applications for this system is vehicle-to-vehicle wireless communications. The other one is Internet of Things, and also this system could be used in the underwater wireless communication and also for indoor positioning. In this talk, I want to go to the vehicle-to-vehicle wireless communication and describe it in the detail. In my laboratory, there are a group of students working on vehicle-to-vehicle wireless communication and another group in underwater wireless communication. Here I want to talk on vehicle-to-vehicle communication in more details. Vehicle-to-vehicle communication is an outdoor application of OCC, and it's suitable for the intelligent transportation system. This system is designed to reduce the traffic congestion and also for reducing the accidents and air and noise pollution. We need a link between the vehicles and between vehicle and infrastructures exist in side of the roads to transfer the data, the information, to reduce the traffic and accidents. At the first, we have simulated this link and we have considered the channel effects as the attenuation and scintillation. We have considered different air condition as the clear, light fog, and smoke with different visibility and attenuation coefficients in our simulation model and in our model. For the turbulence, the log normal distribution model is considered, beside the modeling of the channel and considering different effects in the channel, we have to simulate the receiver. And in the receiver simulation is very important. We have considered different effects, different parameters as the effect of lens and also operation of the image sensor. We have considered different parameters as quantum efficiency, as the different noises, as shot noise, dark noise, and noises in the electronics part of the image sensor. And finally, the intensity of the pixels are calculated. The results is used here. You can see the key parameters, and for example, half power angle of the transmitter and the minimum power and maximum power of transmitters for transmitting 0 and 1 in OK modulation scheme. And also the resolution, the wavelength of the transmitter. At the right, you can see signal to noise ratio versus distance at the different exposure times. Exposure time for the cameras is selected automatically, depends on the background light. It means in the daylight that the background light is very intense, is very high. The exposure time will be low to keep the contrast of the image in an acceptable level. And in the night that the background light is very low, the exposure time increase to have a good contrast. So you can see here that in the daylight that, for example, exposure time is very low as 1 microsecond. You can see that the signal to noise ratio is very low because if we decrease the exposure time, the level of the signal will be decreased, and so the signal to noise ratio also will be very low. So here, if, for example, for us, a signal to noise ratio of 20 dB is acceptable, then our distance should be something like as 20 meters. But at the night that for example, the exposure time increased to 100 microsecond, you can see that the distance, acceptable distance to have a 20 dB of signal to noise ratio increased to 600 meters, and it's very different. It means that ambient light intensity is very important. And we can see this effect in the experimental results also. At the left, you can see the same curves, but for at a different air condition. For high dense smoke, dense smoke, light smoke to clear channel, you can see these results are taken for exposure time of 100 microsecond. And you can see that for dense smoke, the condition is worse. Okay. This is our experimental setup, which is used to study, to investigate the performance of the link. At the left, you see our transmitter, which is the rear lamp of a car, and the modulator for the transmitter. As a receiver, we have used the camera of a smartphone to investigate the performance and to calculate the bit error rate and the signal to noise ratio. We saved the videos on the this camera or this smartphone, and then in the laboratory using a PC, we have processed the videos to take the data and to calculate the bit error rate and signal to noise ratio. The block diagram of the image processing which shown on the videos are shown here. At the first, the frames are extracted from the videos, and then the place of the transmitter on the image is detected by detection of region of interest by an algorithm, and then we have done a synchronization algorithm to overcome the frame rate deviation, and finally another algorithm is used for adaptive thresholding, because due to the change in the background light, the peak-to-peak of the signal change, and so we need to have an adaptive thresholding. And finally, the data is extracted from the frames, and finally signal to noise ratio and bit error rate is calculated. Okay. Here you can see key system parameters which is used in experimental setup. For example, you can see here field of view. You can see here field of view of the camera and also lens aperture. The phone model is depicted here. Also, the LED power is 3 watt, and frame rate 30 frames per second, and bit rate or data rate are 10 bit per second. The resolution is selected very low, and the type of image sensor is a CMOS type, and modulation is okay. Okay. We go to the experimental results. I will show you here some very important results. Tests are done in different conditions, and this one is for indoor applications for in a big salon at the daylight. The curve shows the signal-to-noise ratio variation with the distance, and you can see that with increasing the distance, the signal-to-noise ratio is decreased. For example, in 15 meters, the signal-to-noise ratio is 38 dB, and for 65 meters, it reduced to 20 dB. In other condition, this is for an outdoor scenario and in the daylight. In outdoor, the background light is increased, and so it causes to decrease the exposure time, and the condition will be worse. So we can see that here the change of signal to noise ratio versus distance, and you can see that for 50 meters in indoor we had 38 dB of signal to noise ratio, but for outdoor it reduced to 24 dB. And also we have here the results of bit error rate. In indoor, all of the bits was received successfully without any error, but here in outdoor we have the errors, and so we have calculated the bit error rate. Okay, and other scenario is the variation of signal to noise ratio versus the distance in outdoor, but in the night. In the night, we don't have the ambient light, we don't have the background light. Background light is near to zero, and so the exposure time is very high. And the signal to noise ratio will increase. In this condition, up to 500 meters, we didn't detect any error. We received all of the data correctly. And you can see here that signal to noise ratio for 50 meters is 35 dB, and for 65 meters is 18 dB. Okay. To show the background light intensity effect on the pixel intensity and on the system operation, we have plotted the pixels of the intensity of pixels at region of interest which receive the data versus the time at the morning and at the evening. At the morning, in the right side, you can see that we have plotted it for from 6 o'clock to 7 o'clock, and you can see that the peak-to-peak variation of the pixel intensity changed a lot in 1 hour. You can see that at the 6 o'clock, which the ambient light or the background light is very low, the exposure time is high, and so the intensity variation of the pixels is increased a lot. But in the 7 o'clock, which the sun is in the sky, and the exposure time is reduced a lot, it caused a reduction of the peak-to-peak variation of the intensity of the pixels. So we need a adaptive thresholding system or algorithm for an OCC system, and this is very important. Okay, in the evening is the same also, and you can see that the change of the intensity of pixels or peak-to-peak change of the intensity of pixels. Okay, and finally conclusion. We can conclude that the OCC have the have the potential to provide a practical solution for the optical wireless communication technology. And with the availability of the camera and LEDs everywhere, the OCC systems have a very high advantage in compared to the other technologies. New technologies and future technologies for advanced cameras and image processing algorithms will accelerate the full commercialization of the high-speed optical camera communication technology. And moreover, the current low-rate OCCs also are attractive for many applications in indoor and outdoor systems, communication systems. And finally, we can say that we need a lot of research works to overcome some challenges to have a cost-effective and practical OCC system. And thank you for your attention.
Thank you very much, Professor Golami. It's a very interesting presentation with very nice results on optical camera communication. Thank you very much. The contribution is now open for questions for the audience. Please, are there questions? It's very early in the morning here, so everyone.
I have a question.
Oh, thank you, Professor Gasson. Yeah, please.
It's like a warm-up question, yes?
Yes, yes.
Making people in South America getting ready for the breakfast or just after breakfast, yes. Anyway, thank you, Asghar, for the presentation. And
thank you.
From your point of view, that application of OCC in terms of what we call the killer application, is it mainly in the area of IoT, or is it, for example, in intelligent transportation system? Which area do you think that this will have a major breakthrough in the next, I don't know, 5 years? The OCC, which areas, or which, maybe one area or two areas that you think that it will have a major impact?
Good questions. I think. Okay, do you hear me?
Yes, yes.
Okay. Farid, thank you for your questions. I think that application of the OCC in the IoT, due to in IoT, we don't need a lot of the bit array. I think there will be a good application for the OCC there to use in IoT more than vehicle-to-vehicle communication or for vehicular communication. In the vehicular communication, there are also a lot of challenges that should be solved. But in the IoT, maybe for many of our applications, the moving, we don't need to have the moving, or also we have a low data rate, then I think that this system will be started to use there before than the vehicle-to-vehicle communication.
Okay.
Yeah, I mean, one of the areas which I guess that is becoming very interesting is that possibly using the smart devices, the camera we have, as what we call it, the initiator of the next move. In places like galleries and museums, you go there and there are so many objects. So the camera can pick up the object and use that object in order to link up with the server, to ask the server to download huge amount of information via, let's say, Wi-Fi or standard cellular system. But the camera is picking up some detailed information about the image. Images could be either just the image, or it could be pre-coded images, where it has specific identity. And then the camera will pick this up and then connects the backbone server, the server starts downloading huge amount of information to the smart device. So the visitors can now look on their screen what is happening in the museum, rather than just reading a small print, and they get sometimes tired and so on and so on. And as they could move around the object, it still will maintain the connectivity, because a camera is capturing it and always, you know, seeing it from various angles and so on. Maybe this sort of the application could be sort of very attractive for the art and cultural society, where camera is playing, you know, a crucial role because of, you know, being able to see at the same time to communicate and so on.
Okay, I agree with you, and I think that this system could be used in these situations, in museum, in the maybe different, maybe in the also in the bigger stores also.
Yes,
could be used easily. Okay, thank you.
Thank you very much.
Okay. Are there other questions? Fabian, please. Yes.
Thank you very much for your presentation. I have a question regarding some other challenges when the optical camera communications are used in a very dynamic environment, such as V2X, or for example, we work in underground mines. And it's regarding the problems with the occlusion of when the message is being transmitted, and there is shadowing, for example, in the middle of the message, and also the tracking of the light source. Are there some developments, or how are you dealing with this kind of problems?
Yes, one of the most important challenges of this system is the moving, and moving makes many problems. And maybe when we use more than one camera, for example, in V2X communication, in the new cars, there are more than one camera that is used, and using more than one camera could help to resolve this problem. And also there are a lot of groups that working on resolve the moving problem. Also in my laboratory, I have a group working on the resolve the problem of moving. They use many different methods as the image processing or neural networks for overcome this problem. And yes, this is one of the challenges of this system. And I think that it could be resolved. For example, if we use artificial intelligence, it will help us to resolve this problem when the connection is failed, after the connection is connected. Using these systems, I think we can resolve this problem.
Thank you very much.
Thank you.
Thank you. Please, other questions? Well, if not, I do have also a question here, because Professor Golami, there is also a lot of processing to get out the results for SNR, and also for the bit error rate, and so also for achieving the desired rate, and to get the information out of this communication link. Huh? And how do you see this processing, for instance, in a camera? Because you have to incorporate perhaps these algorithms in your camera, in your processing. So it will also may possibly rise the price of the devices due to this processing. Do you think it's a problem, or that could?
For the processing, I don't think that the camera should process the information or the film, and we need maybe, for example, in V2X communication systems, we need a computer in the, for example, car to process the videos taken by the cameras. And I think that with new processing systems, it's possible, and we can process in real time the videos to take the information. If I understand your question correctly, I don't know.
Yeah, okay, yeah, thank you. So, yeah, Vicent, please.
Hello. Thank you, Professor Golami, for the presentation. I just wanted to ask if in your experiments, have you considered the fact that, for example, in OCC, sometimes you need very short exposure time to see the changes in the transmitting light, but maybe this is not compatible with the exposure times the car camera is expected to use for navigation or just for security. And have you considered this difference? How could it be managed to use the same camera for both purposes?
I didn't hear you, excuse me. I don't have your sound.
You didn't understand?
You need to repeat. You need to repeat your.
Okay,
yes,
I repeat the question. So in OCC, usually you need to change.
Could you please repeat?
Yeah.
Something that I understand,
yeah.
that you asked me about the exposure time.
So
okay, you asked about choosing the exposure time, or in the experimental. No, we use the commercial camera. We use an smartphone camera, and no, we didn't have any control on the exposure time. It was selected automatically by the
default
smartphone. But we know that it depends on the background light.
Yeah, I just asked.
Yes, as you see in the.
Sorry,
yes.
go on. Yeah, I think we're having some connection issues.
Okay.
Yeah.
You see in the results that for the night we could we transmit the data without any error up to 600 meters. But in the daylight we transmit only up to 50 meters, and with error also.
Yeah. Okay. Thank you.
Okay, thank you. I think we can now, with all questions, we can move on to the next presentation. Okay, so thank you very much again for the nice presentation, Professor Golami. So we expect that we can still
okay,
contribution here.
And thank you for giving me this opportunity to share my works here, and thank you so much.
Okay,
bye.
Thank you. So, okay, let's move on to the next contribution here. The next contribution, the title is Content Triggering System Using RGB Strip LIDs and Optical Camera Communication in Rolling Shutter Mode. The paper will be presented by Veronique Jorlet. And there are several authors here, Veronique, Florian of the University of Mons in Belgium, Cristo Jurado on Spain, Sebastian Bette, also from the University of Mons, Belgium, Nicolas Point from Belgium, and also Veronique Moyert, University of Mons and Faculty of Polytechnique in Belgium. So is Veronique here in the audience?
Yes, I'm here.
Yes. Okay, thank you. Thank you. Okay, Vicente, so we can play now the video.
Okay.
Let's go ahead.
Audience, I'm pleased to present you my paper entitled Content Triggering System using tricolor LED strips and optical camera communication in rolling shutter mode. My name is Véronique Jorlette and I'm from the University of Mons. The plan of my presentation is the following one. I will first give the contextualization of my research, then explain why use optical camera communication and give its principles. Afterwards, I will explain the different technical requirements we need to build such a system, and the most important part, the data decoding algorithm. Followed by that, I will present the challenges I faced to build my prototype, and then give some results and conclude my presentation. So first of all, why OCC? OCC stands for Optical Camera Communication, and it's the technology that uses on one side light and on the other side a camera to communicate. Well, first of all, most of our lighting systems are based on LEDs, and LEDs can be controlled to send information. Then why use a camera? Well, nowadays cameras are everywhere. We have reflex cameras, we have cameras on the street for safety reasons, and we also have the camera of our smartphone, which is, I can say it, our eye extension. Then we know that we can use the camera as a capturing tool for incoming light. So now you see where I'm going. We have on one side a light that we can control to send data. On the other side, we have a device that captures incoming light. Then why not build a system based on both? And nowadays, because of the popularization of such cameras, the price is also really low, and we all have at least one in our smartphones. Now, how does OCC work? As I said before, we need on one side a lighting system and on the other side a camera system. On the lighting system, we usually use a LED strip, so a LED ribbon, usually a RGB one, so red, green, blue, that is controlled thanks to a microcontroller. This microcontroller will switch the whole light in different colors at a fast rate so that the eye cannot see the different states, and it will be perceived as more or less white light. We need to be careful with that temperature of light because it should be between 2150 and 7000 Kelvin to appear white. So on the other side, we have a camera. This camera needs to have the rolling shutter mechanism that I will explain a bit after. And this camera is usually a CMOS camera. And what it does is that it triggers each line of its pixel matrix to capture the incoming light and then build an image. But we need more than that to decode the message that the light is sending. We need a microcomputer or a smartphone to be able to process that image and have the message that will trigger the content on our end device. Now I know you're all wondering, how does the rolling shutter mechanism work? Well, as I said before, most CMOS cameras are in rolling shutter, meaning that each line of its pixel matrix is triggered from up to bottom, from left to right. So on the left side of my slide, on the GIF, you can see that the whole LED strip is in one color at different times. Those T1, T2, T3 are the fastest switching time that I mentioned before, so that the light appears white to the end user. On the camera side, thanks to that rolling shutter mechanism, we can capture these different states of colors of the light because it is sequentially triggered from up to bottom, from left to right. So What is the main constraint? Is to have enough switching states on the light side and enough time on the receiving side, on the camera, to have a message in one frame. To make faster the decoding, the image processing part on the end device, we define the region of interest zone to say to the camera, okay, now you decode only that part and not the rest of the image. Now that you understood how to control the light, how the camera works, we need to build a system, an algorithm that is able to decode that image, so an image processing algorithm. So, on the components we used, to control the LED we use an Arduino, and on the end device we used a Raspberry Pi and its camera V2. The first step that we did is to set up the camera. We need to put some key parameters to be able to see enough light but not be disturbed by ambient light. So that's the first step. The second step is to decode the different color components of the image. For that we use some thresholding, and we use the conversion to HSV color space because it's better for the color detection on the library OpenCV. Now that we have segmented our whole image on the region of interest in different colors, we see if we see the right color, so red, green, blue, and we put some constraint on verticality to see if we have a message or not. Afterwards, we have to detect the sequence, so that's step 3. In order to do that, we set a preamble, which is a set of 3 colors. So here, blue, green, blue on the left side of my slide. Then we put the actual code word, so the message we want to send, and then we put an end marker. If our image processing system receives something exactly like that, then it can interpret and trigger the video that we want on our end device. So that's the image of the Raspberry Pi on the down right side of my slide. Building our OCC system was not that straightforward. We faced some challenges, such as finding the right balance of red, green, blue components to have a white light. We had to mitigate ambient light and also study how to make the image better with diffusers. I will now demonstrate you why it is necessary to have a diffuser in front of the light. If I press play to this video, you can see here that the LED cells are not as well defined as before. Indeed, the intensity of the light is not well distributed, and we don't have the nice rectangle that we saw before. That's why we put a diffuser in front of the light. An LED diffuser is typically a plastic semi-tube that we put in front of the light to diffuse uniformly thanks to scattering the light around that. So you can see here on the right side 2 different diffusers, one that have a 56% transparency and the second one that have a 75% transparency. So what we can conclude from here is that if we use the one that lets a lot of light pass through, is that we have some black zones that could maybe do damage to our image processing algorithm. But if we have a diffuser like the first one, we can see that the rectangles are better defined and the image algorithm will be better. I'm sure you're all eager to see our final system running, but first I would like to say here that this is the first LED ribbon and this is the second one. As you can see, they appear white to us, but when I will launch the code on the Raspberry Pi, you will see that both LEDs will appear in red, green, blue components on the Raspberry Pi. So the code was developed in Python. So now the first code word was seen, and we launched a video more on an industrial video that was already stored on the Raspberry Pi. We wait that it finishes. We see the second light, which is a bit harder because it's the second, like a bit the worst diffuser. And we decided to launch a video with the robot. And now I will put it closer for you to see better the image plan of the Raspberry Pi. So here again the robot. And here again the other one, but I will not finish. So I hope that my demo was clear for everyone, and I'm really eager to make a live demo one day at an actual conference. So the main point of my presentation was to present you a functional and robust low-cost content triggering system. It's a really relevant application for location-based information delivery systems, and right now my system can be able to detect about 100 tags, but still keeping in mind that we have to find the right balance so that the light appears white. And another point that I wanted to highlight in my presentation is that the technology is already there and it's not that expensive, and we could really build more systems like this. Thank you for your attention, and if you have any questions, feel free to ask.
Okay, Veronica, thank you very much for the interesting presentation and very nice demo results here. It's very exciting. So yeah, the paper is now open for questions, please. Yes, Vicent, yes, go ahead.
Hi, Veronique. Thank you for your presentation, which is very exciting, as Alexandra said. So I guess this is a very timely research, because Fadi just mentioned the same application would be interesting in museums. And now it's good to see that you're developing something in this same regard. My only question was if you considered, I'm trying to imagine I arrive to a museum and I want to use my phone for this application. I would have to get this the videos beforehand, right? Because the light is only transmitting which video my phone has to play, but before I would have to have it stored, right?
Yes, exactly, Vicente. So my idea was to, so before going to the museum, for example, download the audio guide, so video guide in this case. And so the video would already be stored on the phone, on the end device. And then, yeah, the lights will be the triggers to, depending on where you stand in front of which light in which part of the museum, then the video associated to that location will be triggered. Yeah.
Mm-hmm. Okay, thank you, Veronique.
Thank you.
Thank you. Please, other questions?
You have.
Yes.
Yes.
Yes, Fabian.
Thank you very much, Veronique, for your presentation. I have a question regarding the code, or how you manage to make the light appear to be white, because you have the 3 different colors turning on and off constantly. So how did you equilibrate, or how was the procedure that you used to equilibrate the 3 colors to make white from RGB?
So what we did is, on one side, we tried to see the limits up to which we can switch the light without seeing the different states. So for example, at a switching with 100 states per second, or even less, like at 60, you already don't see the different states, only with the camera. And on the camera side, on one side, we made like a trial and error, trying to see how many states we can see per frame. And we also computed how much time it takes to have one frame. And then by checking how much states we want to see and how much time it takes to have one frame, we computed enough time to have at least 9 or about 12 states. And because our message is a bit smaller than that, we were sure that at least in one frame, we will have the message we want to decode. I put the exact numbers of the timing in my paper, but right now I cannot remember exactly the timings, but it's in the paper.
Okay, so you didn't use a code, so you can somehow make stable the time that you put one color to make the things appear white.
So to make it appear white, there is not really a constraint. Even if you switch only red, green, blue all the time, you will see that to your eyes, it will appear more or less white. For example, in my application, we used the 2 code words one appeared more white than the other and the other one a bit more blue, but that's really depending on the message you're trying to send. I hope it replies to your question. So if you switch the 3 components at a fast rate, it will appear more or less white.
Okay, thank you very much.
Thank you.
Okay, yeah, thank you, Veronica. Are there other questions?
I have one question.
Yes, please, Cesar.
Hello, Veronique. Very nice presentation. And I have two really easy questions, actually. First of all, I don't remember if you indicated the distance between the mobile phone and the transmitter. And secondly, I don't know if you guys tested what happens when there is shadowing or obstruction between the camera and the LED. Could you tell us what happened in that case? Did you lose completely the communication link?
Sure. So to reply to your first question, I didn't mention it in the video, the distance between the emitter and the receiver. So we know that we measured that we needed at least 1 meter between both to have at least one entire code word in one frame. Otherwise, if you get too close, then you don't see as many different states of light, because because of the projection of the LED strip on the camera image, you need to have at least a small distance to be able to see the whole code word at least once. So the minimum is 1 meter, and then you can go up to a bit further, but we didn't try to go up to 6 meters, for example. We were always between 1 meter, 2 meters, keeping in mind that the setup would be like in a museum, that you could have at least 1 to 2 meters, 2.5 meters, and it could still work. And regarding your second question, so what we did at the beginning, we used nothing in front of the LED strip, and we could see that the center of the LEDs were too bright, and we couldn't really decode well the image. So that was the first video I presented. And then we studied different kind of diffusers that we put in front of the light. We saw that if we put like only a transparent sheet, it was not working that well because the diffusion was not enough uniform. Then we put a plastic tube that was working really better. And then we even saw that depending on one plastic tube, depending on the other, it was not, the image was not built as well. So we make some measurement to see which kind of diffuser was the best. But then further away, we put like a white paper sheet, and that was still more or less working, but not that great. But I guess that if you put like a big obstruction, then it will not work. That's why we really imposed a region of interest in which the image had to be clear. Otherwise, we cannot decode the message. So we don't actually scan the whole frame, the image frame. We just put like a region of interest that appeared like a small rectangle at the middle of the frame of the Raspberry Pi, and then we impose that the LED strip has to be in that zone to be decoded. So if there is a big obstruction, thank you.
Thanks for answering the question. It's clear to me. Thanks.
Okay, Veronica, thank you. I just have a simple question. Are these diffusers, are these off-the-shelf components, or the diffusers have you designed and built them for your experiment?
No, so every equipment we use are off the shelf. So I went to the local, I don't know how to say it in English, a construction shop where you can buy LEDs, apertures, and things like that. We bought several ones, and then we made the measures with an optical power meter and tried to see also on the camera side which one was the best diffusion and gave the best image. And yeah, so everything was off the shelf.
Okay, thank you. So if there are not other questions, or so Veronica, thank you very much once again, okay, for the contribution, and also the audience for the questions. Let's move on for the next presentation here. The title of the next presentation is Visible Light Communications for 6G Wireless Networks. Okay. And that will be given by Eleni Niarko. Is that correct, if I have pronounced the name correctly? So sorry. And it's a contribution from the University of Peloponnese, and also from Professor Gassemloy at Northumbria University, and Professor Luis Nero at the University of Aveiro. Okay, please go ahead. Let's play the video then. Okay, thank you.
Hello everyone, my name is Eleni Niarchou from University of Peloponnese in Greece, and along with Professors Boukouvalas, Gassemloy, Halves and Svanovic, we would like to present you our paper on VLC for 6G wireless networks. In the introduction, the technical aspects are identified as well as the research challenges which have raised the need to evolve from 5 to 6G. In the second section of the paper, we present a vision of 6G technology, focusing on its proposed requirements of future communication applications and scenarios, the possible network architecture, and its key performance indicators. The third section describes VLC technology, features that support its use in 6G networks, service application, and the research challenges that may contribute to the innovation and development of VLC. Given the enormous potential of the fifth-generation networks and their foreseeable evolution, is there a real motivation for thinking of the next-generation networks? The answer is yes, because 6G is intended to provide solutions for the technological limitations of 5G by extending the scope of capabilities in support of increasingly new and innovating applications in truly smart environments. The evolution from 5 to 6G can considerably overcome the challenges of ultra-low latency and high reliability, providing very high bandwidth for communications. This study aims to contribute to the innovation and development of VLC by opening new areas of research for 6G, and thus new advanced services will be provided to the users in the future. However, these new applications have increasingly demanding requirements, which are difficult to be fulfilled in 5G. Firstly, mission-critical applications such as robotics and autonomous systems need ultra-reliable low-latency communications. Secondly, 6G is being developed in response to the increasingly distributed radio access networks and the need to offer much higher data rates utilizing the millimeter wave, terahertz, and optical spectrums. Thirdly, connecting autonomous vehicles demands unprecedented levels of reliability and low latency even in ultra-high mobility scenarios to guarantee passenger safety. Key performance indicators for 5 and 6G technologies are outlined in table below. Note the high data rate of 100 Gbps and a low latency of 0.1 milliseconds for 6G are highly desirable in many applications, including vehicular communications, virtual reality, to mention a few. Despite the fact that it is unrealistic to accurately predict what and how the future network architecture will be, the architectural changes associated with 6G will be categorized in infrastructure, control, and networks as shown in figure. From the infrastructure point of view, the target of 6G network is to provide full wireless coverage. As far as the control is concerned, the design of 6G network architecture should consider possibilities of artificial intelligence (AI), that is machine learning, as the endogenous characteristic. In the case of networks, an enhanced stratification will consider the use of multiple technologies including millimeter wave, terahertz, VLC, dynamic spectrum access, blockchain, management plane, content-driven routing, and 6G applications. VLC is considered as a potential complementary technology that can be adopted in 6G, can offer a huge license-free bandwidth, high level of security, low costs, and no radio frequency (RF) induced electromagnetic interference. VLC can be used in many applications as shown in the figure. To begin with, VLC can be used in smart environments, smart homes, healthcare, to handle the massive data transmission, to improve security and energy efficiency significantly. Regarding smart healthcare, could be used to minimize health risks associated with RF radiations, for heart monitoring, electrocardiogram, blood pressure, for machine-to-machine communications, and patient record keeping. The already available infrastructure of lighting, street lights, parking lights, can be utilized to provide high-speed, low-energy, and sustainable network connectivity, smart monitoring of road accidents, and forecasting traffic in smart cities. Vehicle-to-everything is a key enabler for autonomous vehicles, which holds great promises in improving both road safety and traffic efficiency. Regarding the localization, LED sources and a smart device with a built-in camera or a photo detector could be used for highly precise positioning, less than centimeters, in indoor and underground environments for the location of devices, people, objects, for both data communications and navigation. Augmented reality (AR) extends human sensor capabilities by utilizing more information, audio, video, images, with high applicability in smart environments. AR can offer new opportunities at the application layer level by adding a virtual layer, including video, image, sound, to the real environment. The combination of VLC and optical camera communications (OCC) technologies, together with the machine learning or deep learning with neural networks, can best support AR in indoor environments. Underwater VLC (UVLC) has the advantages of low cost, high transmission data rates, strong anti-interference ability, and high security, thus making it highly desirable in underwater environments. VLC with OCC can be combined with mobile computing to realize novel forms of sensing applications in smart environments, for instance, sensors which can detect and send data information concerning oxygen, carbon oxygen levels, or temperature in the environment. Integration of VLC with existing communication standards is necessary to support the efficiency of network development. The downlink in VLC consists of the transmitter, known as a VLC access point (VAP), and the power line modem to connect the transmitter to the network. To connect all the VAPs globally, a power line communication (PLC) technology is utilized, but the dense deployment for illumination purposes and the cost will be increased, and PLC may be limited by interference of wireless connections, low data rate, and additional cost of integrating with VLC. The downlink VLC transmission can be received by users either through a photodiode or an image sensor, but for the uplink either VLC, Wi-Fi, or infrared links could be utilized. In addition, the emerging AI will provide new challenges. On the downlink VLC connection, on the physical layer of the receiver part, deep neural networks (DNN) can be used for channel state estimation and signal detection. In addition, on the transmitter link and the network layer, neural networks have been applied for mobility prediction, traffic prediction, and traffic control, respectively on the uplink. It is challenging to provide bidirectional downlink and uplink channel design by using LEDs, because it could be aesthetically unpleasant to the user and consume a lot of energy. In this case, another technology, such as infrared, could be a potential candidate, which leads to the realization of a high-fidelity network. Li-Fi are designed to work seamlessly with the RF wireless networks, can provide high data density wireless communication services to multiple mobile users, and can support handovers. One of the main challenges in the 6G area would be the maximization of achievable data rate. VLC has a huge potential for further development and improvement in the next decade, catching up with the current performance gap between VLC and 5G technologies with already demonstrated gigabps data rates, and will be reaching the terabps range for use in 6G services. In wireless links, using the same transmission resource will interfere with each other most vividly in RF technologies and less in optical wireless systems. In the downlink, the VAPs in the same area would introduce interference, leading to lower signal-to-interference and noise ratio (SNR) at the receiver, and hence performance degradation. Whereas on the uplink, the users in adjacent cells may share the same transmission resource, which may experience co-channel interference (CCI), and when the same transmission resource is reused by the users within the same cell, experience intra-cell interference (ICI). In mobility scenarios, the users can maintain their connectivity while switching cells through an automatic and seamless handover. Mobility and handover management are probably the two most challenging issues in 6G networks. The vertical handover between the radio and optical wireless networks has been studied in the past. Network handover is necessary to provide secure, safe, and uninterrupted service. A good vertical handover scheme has been proposed to maximize the quality of experience of the user. Last but not least, one more major challenge in VLC is the dimming, that is, operability under low or no illuminations. The key point is operating LEDs at very low dimming levels and still maintaining the transmission performance, that is, quality of service. Dark VLC also provides a new ultra-low power, always-on connectivity affordable for mobile, and also enables communications for Internet of Things devices. In conclusion, this paper discussed the potential use of VLC within the 6G platform and the challenges it faces. Some technical aspects suggest that VLC is compatible with 6G, but there are still many challenges to address. Thank you so much for your attention, and I'm willing to answer to your questions.
Thank you very much, Eleni. Okay, the paper is now open for questions. Are there questions or? Okay, Eleni,
can I just make a comment to just encourage our younger generation to
yes.
get involved with this event?
Okay.
I mean, the presenter put hours and hours of effort to obviously prepare the slides and so on and so on. No presentation can address everything within the, sorry. And therefore, it's important that younger generation do ask questions from the presenters, at least to give them an opportunity to think about issues, and hopefully they will be able to do further research and investigation as part of their future research in order to address some of the concerns, technical concerns we have. So these platforms are really vital for younger generation to practice their academic and engineering skills of basically getting engaged in science and engineering by, you know, really asking basic and fundamental questions. And if you don't use this platform to do it, then you know there are no other platform for us to basically exercise that what we are supposed to do at the university level. That would be my advice.
Thank you for the comment, Ferry. Thank you. We have a question here by Fabian. Yes, please.
First of all, also following the words of Fari, we have our YouTube channel. So if someone wants to ask a question by YouTube, we can read the message. You can write the message there, and then we can ask here in the Zoom meeting, or transmit the question to the author of the paper. And I have a question too for the author of this paper, and it's about how do you think it will be VLC if you think that 6G or next generation of wireless network will be finally the generation where VLC, Li-Fi, all these technologies will be available in a commercial manner. Will be the key, or finally we will see VLC not everywhere, but at least starting to be deployed in the next generation wireless network?
Yes, definitely. VLC has many opportunities. Light is everywhere. We have lights in our rooms. The lights are everywhere. We can use these opportunities for communications, for illumination purposes, to combine everything. And yes, I believe it has great opportunities in the future. Can support many things.
Okay. Maybe I could just come in, because as one of the co-authors, that I mean, this is $1 million questions that which is being asked, which is interesting question, yes. And it's very difficult to answer these sort of questions, especially when we are an academic, because our academic role is driven by our curiosity. The curiosity is the engine for us to look for new ideas. Industry plays the roles of converting ideas into businesses and making money out of that. How it happens, I don't think there is any particular rules and regulations and procedures or algorithm. But we look at the past history, and when we look at that pattern of how ideas, all of them definitely, yes, but how ideas in general converted into businesses, we learn a lot of things from that pattern. And then on top of that, we have not only the business pattern, which is driving us. As you know, the last 2 weeks in city of Glasgow, 140, 150 leaders or representatives of governments have been gathering in order to address the global warming, carbon emission, energy usage, and so on and so on. These are the indicators that we see in our day-to-day lives. And therefore, as engineer, we need to basically raise our awareness that what does that mean to us as an engineer? Because we cannot isolate ourselves from what is happening in the world and just focus on developing algorithm or designing circuit and so on. So our social values and engineering values are basically largely driven by the society, the impact on society have. So that indication is telling us that there is a surge for growing demand and pressure by young people that we should look for technology which is sustainable and uses less energy, and therefore the temperature target of 1.8 degrees or 1.5 degrees by 2030 is maintained. Now, how do we do this? Do we do it by adopting this form, established philosophy in wireless communication, or do we push forward that we have to break away and we have to look at what resources we already have in certain areas and therefore utilize that in order to reduce the carbon footprint, reduce the energy uses? If we do this, then you can see the role of, for example, light-based communication, whether it's infrared or visible. You can see that how important the role they play. And therefore, we have to drive this through. And that's our role as a researcher and engineer and scientist.
Okay, thank you. Thank you. We have a question here by Vicent, and then after by Pablo, please, Vicent.
Sorry. Yeah, I just wanted to mention that, as Fari said in the beginning, this is the paper, the last paper of our dear Professor
That's right.
Anthony.
That's right.
And yeah, I just wanted to stop for a minute to also congratulate Eleni for this effort she made in this presentation, which is a compilation of all the prospects we have for VLC in the 6th generation. And for those who are wondering, because Anthony was her supervisor, and so from here in the Canary Islands with Professor Rafael Jimenez, we're making an effort now to include her in our program, and we are hopefully getting a scholarship for her to move with us and continue her work. In this case would be in OCC, and I have worked in the past in OCC for wireless sensor networks, so I guess it's going to be in the same line. And yeah, for all of you who are wondering what will happen with her, we are making this effort, and I want to congratulate Professor Anthony for all his legacy that he began as a pioneer in our field, and we owe him so much because as Fadi mentioned, they organized one of the first conferences in IET, and they couldn't imagine we would be today all over the world, right now in South America, in the past in West Asia and Europe, of course. And it's great the effort they have put. As you see here, it's almost 40 years of working for this. And yeah, I just wanted to mention this contribution of Professor Anthony.
Thank you. That was very nice words.
Yeah.
Yeah.
Thank you. Pablo, comment?
Oh, yes. Good morning to everyone. I was wondering if all these applications will remain mostly for indoor environments in the future, or are there any advances trying to overcome the issue of outdoor? That's my question.
Yes, of course, there are applications for outdoor as well, for smart cities, for vehicle-to-vehicle communications, underwater communications. It is a potential application technology. Of course, VLC has applications both in indoor and outdoor scenarios.
But all these applications have been thought to remain indoors so far, or are there current efforts to overcome, or?
Maybe I could, I think I just got to chip in. Yes, I mean, it started from indoor, it's definitely is moving outdoor, and certain outdoor application. I think this is the only technology that you will have, especially if you look at what 6G is trying to do in the next, beyond 2030, where all the wireless communication networks is up in the air, almost like breaking up what we had from 1G up to 5G. And within that framework of mind, and especially in urban and rural areas where high density of devices and people is there, then therefore we have to look at ways of doing it and so on. And therefore, yes, it certainly, in my personal professional view, that this will definitely move outdoor, and there's no question about it.
If you allow me, may I ask you if you in UK is there any trial on 6G going on in the moment, for instance, or
at the moment? No. Maybe my colleague is Alexius. I can see here from Finland, because they are far advanced as a country in 6G. Maybe Alexius can make a comment on that. In UK, we haven't, although people are talking it. Alexius, if you are there, maybe you can switch on your camera and say more about it. Okay, some of the Scandinavian countries have been far in advance in this area than the rest of the world.
Okay, sorry. So I think we are a bit late on time here with the next presentation. I will ask Cesar for putting the question to Eleni, perhaps over the email. Okay. And let's move on to the next presentation here, so that we do not get late. The next presentation, the title is the sum sequence rate of NOMA-enabled visible light communication network with the random wave point mobility model. It will be presented by Fatme Bahadori and Sayed Sadhu from the Sacvlc Behesht University, Iran, and also with a contribution co-work of Professor Fari, of Professor Zabi Gassenloy. Sorry, I'm not. I apologize for not pronouncing correctly the names of the authors. But let's move on with the playing video. I think Fatime is around, isn't she?
Yes, I'm here.
Okay, thank you. Let's go on then.
Hi everyone, I'm Fateme Bahadouri from Shahid Beheshi University. It's a privilege to take part in the third Sacvlc conference. I will present you a recent paper entitled The Sum Sequence Rate of NOMA-enabled VLC Network with the Random Waypoint Mobility Model. Having a glance on what I'm going to present, these are the main parts of the presentation which I'm going to speak about one by one. So let me start with the introduction. The story of VLC begins with the spectrum scarcity in the radio frequency, the increasing licensing fees of the RF spectrum. In addition to that, the emergence of digital transformation in industries, businesses, and people's daily lives has led to a tremendous growth in the number of devices being connected, with the need for high-speed communications networks with new wireless technologies. These strong trends are the main motivations for the birth of optical wireless communications. Narrowing down the subject to the physical layer secrecy of VLC systems, it is good to know that these systems, compared to their RF counterparts, are inherently more immune against interception and other secrecy threats, which this feature comes from the nature of the light that doesn't penetrate many obstacles like walls. However, complete secrecy is not naturally guaranteed, and because of the broadcasting nature of the VLC, addressing the secrecy issues in VLC systems is of high importance. Actually, the literature around the subject can be divided into two main categories of information theoretic and signal processing areas. In this slide, I would like to present you a big picture about the different scenarios of what is already done in the literature in the area of PLS in VLC. The number of papers that have gone for this particular subject is more than what is presented here, but actually, I can claim that the considered scenarios are covered here. Categorizing the scenarios by the number of the APs, legitimate and illegitimate users, and the mobility model for them, the first paper in the table has considered one AP, one legitimate user, and multiple illegitimate users with the uniform mobility model. The second one has extended the number of APs, and the third one has considered the relay in the network while simplifying the mobility model. Finally, the last paper in the table has considered the cellular setup and has extended the number of users and APs while considering a uniform mobility model for the legitimate users in the cells. To make the long story short, here in this paper we have considered a multi-cell network with multiple number of users with NOMA-enabled transmission. The innovative part of our assumptions are actually threefold. All of the users, say legitimate and illegitimate, are moving based on random waypoint mobility model. The scenario is not restricted to a limited number of illegitimate users. And the last but not least, we are customizing one of the off-the-shelf resource allocation techniques named gain ratio power allocation. Coming to the system model as the next section of the presentation, the system model is provided in this slide, which is a combination of PLS in a cellular VLC network with NOMA access and RWP mobility model for all users, where the latter one makes the considered scenario more realistic. As I said earlier, our system model includes M access point position on the ceiling and multiple users located within the cells randomly. As shown in this figure, there are overlapping regions between the cells to ensure sufficient illumination levels. Here, the users are actually divided into different groups, with each group being assigned to an AP. The legitimate users assigned to the AP are the potential eavesdroppers to the adjacent cell depend on their temporary location. So, eavesdropping takes place within the overlapping region. In this slide, we see the well-known VLC channel model as used in this paper. And here we have its equation and the main parameters such as the FOV, the angle of irradiance and incidence, the Lambertian order, and so on that have crucial roles in the system performance. As I mentioned earlier, according to our considered scenario, each user can act as legitimate or illegitimate user depending on its temporary location. So it would be two kinds of receiving that we classified as receiving and eavesdropping phase and formulate the SINR in each separately. In this slide, I would describe how we formulate the SINR in the receiving phase. The SINR for the jth user associated with the ith AP in its receiving phase is expressed as this equation, where Hij is the channel gain between the ith AP and the jth user, Pij shows the allocated power from the ith AP to the jth legitimate user, sigma ij2 is the variance of AWGN for the jth user, and beta ICI is actually the intercell interference coefficient that would be 1 or 0 depending on the users are in the overlapping area or not. IJ-ICI is the NOMA interference from the adjacent AP, and at last IJ-NOMA is the NOMA interference in the jth user. But what happened with the eavesdropping phase? The eavesdropping SINR is expressed as this equation, where Hi'(E) is the channel gain between the I'(AP) and the eavesdropper, Pi'(J) shows the allocated power from the I'(AP) to the jth user, and in this case, we should note that as the eavesdropper is always located in the overlapping region, beta ICI would be always equal to 1. And IJ-NOMA shows the NOMA interference at the eavesdropper associated with the jth legitimate user within the coverage region of the adjacent cell. And the IE-NOMA shows the residual interference from the receiving performance of the eavesdropper within its own cell. Two main assumptions that we have considered in this work is weak interference law and non-cooperative eavesdroppers, which I will describe them in this slide. Based on the weak interference law, as we can see in this figure, the secrecy rate of the users that have channel gains smaller than the eavesdroppers would be equal to 0. Non-cooperative scenario means that if more than one user associated with one AP is in the overlapping area, then the user with the highest channel gain to the adjacent AP is considered as the stronger eavesdropper, and that would be the main eavesdropper. As a result of the dynamic movement of the users of their instantaneous locations, each user can act as an eavesdropper to its neighboring cell. So, based on the users within the overlapping area in each time frame, there will be different cases to formulate the achievable secrecy rate. In the following, I would describe each case separately by considering only two adjacent cells. In case 1, as can be seen in this figure, there are no users in the overlapping area, so the achievable secrecy rate using the SINR equations described in the previous slides is given by this equation. And I should mention that in this case, the beta ICI would be equal to 0. But in case 2, there are one or more legitimate users assigned to AP1 or AP2 within the overlapping area. As shown in the figure, no user associated with AP2 is acting as eavesdropper to the users in the associated cell with AP1. Thus, the achievable secrecy rate for the users in the coverage area of AP1 is as the equation we write for the case 1. But the difference in this case is that the beta ICI would be equal to 1 in this case. And with AP1 users in the coverage area, the achievable secrecy rate of users in the coverage area of AP2 would be equal to this equation. In case 3, the legitimate users of both APs are in the overlapping area, so both group of users will experience eavesdropping, and the achievable secrecy rate is given by this equation. But in order to allocate power to the users, gain ratio power allocation method is employed. In this method, we would first sort the users' channel gains in an ascending order, then allocate power to the jth user based on the equation showed here. So, in this method, the users that have stronger channel gains would have a smaller portion of the total power. We also, to modify this power allocation method to our considered scenario, add some steps to avoid allocating part of the transmit power to the users with secrecy rate equal to 0. In this regard, in each time frame, by following the ordering of the legitimate users' channel gains, we first determine the stronger eavesdropper, and then, assuming weak interference law, we remove the users with channel gains smaller than the strongest eavesdropper. And the following steps are the same as the GRPA method on the right hand of the slide. In the following, I would present the simulation results for the proposed NOMA VLC network with modified power allocation scheme. To this purpose, we have used the average network sum secrecy rate, which is defined as this equation, and the main parameters we have used to simulate the proposed problem and their associated values are depicted in the table. This figure shows the average network sum secrecy rate as a function of the transmit power for the conventional GRPA and the modified GRPA methods. As can be seen in the figure, the average network sum secrecy rate increases with the transmit power, and for an average NSSR of 10 bit per second per hertz, the gain in the transmit power is equal to 2 dB for the modified GRPA compared with the conventional GRPA. And also the power saving becomes marginal for lower values of the average NSSR and scales for the higher network sum secrecy rate. In this slide, we have the effect of the FOV and half power angle on the network's performance. Figure 6a illustrates the effect of the FOV semi-angle on the NSSR with respect to the transmit power for the modified GRPA method. As can be seen in the figure, the network sum secrecy rate improves where the FOV decreases, and it's because larger values of FOV results in higher ambient noise level being captured by the photodetector. And figure 6b indicates the effect of the half power angle on the network sum secrecy rate in the presence of modified GRPA method. And it shows that network sum secrecy rate improves with decreasing the half power angle, and it's because that narrowing of the optical beam of the LED actually results in suppress the inter-autocell interference and also the network secrecy performance improvement. At the last part of the presentation, we have the conclusion part. Actually, in this work, we calculated the achievable secrecy rate for the users in 3 possible scenarios. Power allocation for the mobile users was formulated to optimize the secrecy rate for the network, and the well-known gain ratio power allocation method was efficiently modified. Also, the simulation results showed that the average network sum secrecy rate is improved by using the proposed modified GRPA method, and the results also indicated that the average network secrecy performance is improved by decreasing the FOV and half power angle of the optical transceivers. Thank you for your attention.
Okay, Fatima, thank you very much for the interesting contribution, challenging also simulation. Thank you. So the contribution is open for questions. Any questions from the audience? I do have a question, Fatima. When you present your results, the power, the allocated power in the x axis I think it's pretty high, because it goes from 0 dBm up to 12 dBm. Do you think it's an acceptable power for using in your, for instance, in your nodes there that you when you do the simulations?
Thank you for the question. Actually,
Sorry. Oh, I think there is a problem with the connection. Hello?
according to the articles, could you hear me?
We still cannot hear you. I think there was a problem with the connection. We couldn't get the answer.
I think the
Oh yeah, it's better now. Please. Hello. Hi guys. Are you listening?
I don't know. I think they have a bad connection, isn't it? Yes.
Yes. Yes.
I think that the answer to the question is that the power is quite reasonable power. Yes.
Yeah.
So. And then it depends on really whatever light sources you have, and probably what height you want these light sources to be. So therefore, that can be changed depending on the type of the light source, its illumination area, the height, and so on. So those are, but if you look at typical standard high power LED or low power LED, I think that should fit in within the range of existing devices, and so I think it should be no problem.
Because you should really be constrained perhaps with the at the lower power range, not at the high, because you won't find LEDs with such very high powers.
True. I mean, you can constrain it. You can, and I guess that when you do the proper link budget analysis, when you're designing the systems, and yes, if your system can operate at the lowest power level, don't forget. This is very important that in our community we keep. Sometimes we're forgetting it. The whole concept of the VLC starts from this point, that VLC is based on LED, which is used for illumination. LEDs are not used for data communication.
Yes.
That's not their purposes. If we do that, then this is not what VLC is all about. First comes illumination, because that's why they are there in the ceiling. Yeah.
That's right.
So therefore, depending on what architects have put on the ceiling, we have to use that. We are not an architect. We may recommend in the future that, maybe they should use this sort of LED, but that is the whole point, that it uses the existing lighting infrastructure based on semiconductor devices, which is LED or laser in outdoor. And therefore, and there are a range of them. It's not like RF antenna that we can design and say that, oh, we have to put this antenna. No, architects will decide what light they will use. That is their domain. Yes, we can advise them.
Yeah.
And if they listen to us, fantastic. If they don't listen to us, they will not listen to us.
Yeah, I think you're right. I mean, we are most constrained by their design.
Absolutely, and that's the beauty of it. That we are working with architects.
Yes.
To provide them additional functionality, not that we are operating separately from architects or building designers.
Yes.
Because they will not listen to us. What you say is, no way, we are going to do this.
Okay, so thank you very much. So let's move on. So we are a bit late. Fabian, please, if you have a question to Fatma, you can ask over the email, please. Okay. So the next presentation is an invited contribution by Professor Ana Maria Veni. The title is Exploiting Visible Spectrum for Localization Service in Future 6G Networks. I just read Professor Svein Ana Maria biography. Ana Maria Vein is a senior member of IEEE, is a tenure-track assistant professor in the Department of Engineering at Roma Tre University, Italy, since March 2020. She received the PhD degree in biomedical engineering, electromagnetics, and telecommunications from the Department of Applied Electronics at the Roma Tre University. She received the first and second level laureate degree, cum laude, in electronic engineering, also at the same university, respectively in July 2004 and 2024 and 26, respectively. In 2009, she was visiting researcher in the Multimedia Communication Laboratory, directed by Professor Thomas Littrow at Department of Electrical and Computer Engineering, Boston University, USA, where she worked then on vehicular networking through the use of visible light communication. She's a member of ACM and IEEE senior member. In March 2018, she got the Italian habilitation for associate professorship in telecommunications engineering. She's now involved in the organization of several, she has been involved in the organization of several IEEE and ACM International Conference, and is a member of the editorial board of IEEE Communications Magazine, Ad Hoc Networks, Journal of Networks and Computer Applications, NanoConnect, Elsevier journals, IEEE, JCN, ITU, JFET, and ETT Relay Journal. Her main interests are VLC systems, wireless ad hoc networks, and Internet of Things. Professor Ana Maria, please, the stage is yours. Thank you for participating. I think you can. We can now play the video. Vicente?
Good morning, everybody. This is Anna Maria Vegni from Roma Tre University in Italy. In this presentation, I'm going to talk about the use of the visible spectrum, so the visible light communication for localization services in future 6G networks. In order to answer to the main question that can rise, that is how the visible light communication can be useful for next generation networks, we have to identify, first of all, the main needs and requirements for a next generation network. With this aim, we have first to focus on the current situation, so the technology that are used nowadays, and identify a route towards the 6G. After that, we can better identify and focus on the role of visible light communication, and in particular on localization services. Particular attention will be also provided to the use of machine learning for visible light positioning, and then we can conclude the presentation by taking some outcomes and the results. So let's start with the current situation. So this is the picture of the forecast of the threshold of traffic per month that can be generated in the next few years. As we can see, by 2030, there will be an increase of devices, of wireless devices, reaching around 100 billion of devices that will overcome the zettabytes per month threshold. So this means that in 2030 we will have a very huge amount of generated data that will be forwarded, disseminated, and transmitted all around the network. So how can we manage all this amount of data, all these new devices, we have to increase the requirements of data networks. So first of all, we have to increase the available data rate, the data rate per use that should be up to at least 1 terabit per second. Terabit per second, so 10 power to 12 bit per second. That is a very, very high requirements. Then other requirements are related to the latency and the reliability, that both will be the reliability should be very high, around 10 power to minus 9, and the latency as well should be very, very low. And so we are talking about around 0.1 millisecond. This is because we did all this amount of data, all this amount of devices, so we are talking about massive devices, we should have we should guarantee very high efficient performances. Given these few numbers of main requirements, let's now see what will be the path, the route towards the 6G generation. So first of all, we can talk about a generation comparison, you know. So looking back to the first, the second, but let me say better is to see to look at from the third, since the third generation up and forward, we can understand that there is always an increase of bandwidth needs, data rates need, and latency needs. This is because there are a lot of devices that are increasing. There is a lot of new services, new applications. So we are not only talking about internet browsing, instant messaging and something like that, but we are envisioning new services that several years ago were not possible to consider. So for instance, the navigation and the tracking of people or of vehicles, this is something that needs very low latency and also high data rates, because we can envision new applications. Regarding the 4 and the 5 generation of cellular networks, we can observe that there is always an increase of this covered area. So this is the spider graph depicting different KPI for 4G, 5G, and the next generation network. And so we can observe that always from 4G and 5G there is an increase, but let me say also 4G and 5G have very similar performances, but what we want to achieve is that in the next generation the data rate should be very, very high. So not more talking about 110 gigabit per second as for 5G, but we want around 100 gigabit per second. Same consideration applies for latency, spectral efficiency, mobility, reliability, and something like that. This is the main route. What will look like the 6G scenario? In the 6G scenario, we don't have to talk about a single network, but about an overlapping of different networks. So we have very well-known networks, ground networks, so cellular networks, vehicular networks, indoor networks, and something like that. But at the same time, we should also consider other at the same level the ocean networks. Ocean network, or also called as underwater networks. So all these the communication among devices that are behind underwater. And here there is also a set of new applications. So, for instance, the tracking of divings or the monitoring of underwater and something like that. going up, we will have the area and space network. So in these two layers, we are observing an increase of new devices. So for instance, in an area network, there is an increasing of smart devices such as the UAV, drones, so these small devices that are flying and work all together, collaborating for common task. And at the same time, we have also bigger devices such as the HAPS, the high altitude platform systems, helicopters, and something like that. And then we have also the space networks with traditional GNSS, but also let me say about more specifically LEO constellation. So for instance, the already operative SpaceX constellation, something like that. So connectivity in this scenario will be a kind of a 3D connectivity where different overlapping net layers will collaborate, will cooperate all together for a common task. The main application of next generation networks, there will be an increase, an integration of intelligence, passive networking, together with the precision localization and high resolution sensing. So the main application that can respond to all these new requirements can be autonomous vehicles that need very high localization accuracy and low latency, and also healthcare, new healthcare system, for example, for high precision surgery, precise agriculture, smart agriculture with the use, for instance, of UAV devices that can be monitor the ground. Also the application of virtual reality and augmented reality that requires high data rate and low latency, and also high accuracy as well. So in order to respond to all to these needs, new application and network architecture, we have to consider the role of visible light communication. This is the second point of this presentation. So this is the this picture is very intuitive because it represents the three main pillars of 6G networks that are enhanced mobile broadband, low latency and high reliability communication, and massive communications. In these three, in this triangle, we can observe the new applications. So starting from very high speed connectivity application, augmented reality and virtual reality, that both requires very high data rates. And so in this case, a visible light communication can be a killer technology because it provides gigabit per second access. Regarding the high accuracy requirements, we have autonomous vehicles and more in general all the smart hospital, since for instance smart surgery is a very important aspect, and in this case visible light can be very useful and very eligible for these particular scenarios. Also, the aspect of security, since we know that visible light is a secure technology, all the application of smart home, smart office, smart city, and something like that can be provided by a secure visible light communication. Okay, so let's now go deeply into the localization services provided by visible spectrum. What will change in the next generation network? So, first of all, we have to say that traditional sensing and localization using, for instance, GNSS or cell coordination system will become obsolete because for different reasons. First of all, the application is going to be changed. I mean, it's not that it's a GPS-based application because simply I want to track, I want to know where I am, but I want to know where I am for a particular scope. For instance, in case of intelligent connected vehicles, is not. I don't need to know the exact the precision by means of GPS, because the GPS provides an accuracy of 1 meter, 15 centimeters, and not lower. But I want to be very sure to where I am, because I need to transmit, to retransmit, disseminate messages with a very precise localization. Also, the case of tunnels, or let me say more in general, harsh environment where GNS signal is not available, we have to consider other technology that can provide this information. This is a picture that represents how the accuracy change for different applications. So in case of, for instance, of navigation, pedestrian navigation, so also in the case of contact tracing application, for in case of pandemics, we need an accuracy of around not lower, around 1 meter, and this can provide in case of coverage, higher coverages. While, for instance, in case of machine industry, so robotics, Internet of Robotic Things, we need an accuracy that is very lower in terms of error. Okay, so the high accuracy, because we want to be very precise and accurate, and this is, for instance, the case of smart surgery applications. Okay, so let's now provide a few examples of how visible light can provide these very low accurate, low error, emission error, in case of indoor and underwater, for instance. So let's start with an indoor scenario. These are some solutions, some results coming from this work, and this is represent a localization estimation in case of an hybrid approach that consists of both a radio receive signal strength and also a time difference of arrival. I don't want to talk about the metrics and how it works exactly, because I think that this is something that is well known by the audience. But let me say that hybrid metrics, I mean, with the use of, for instance, radio signal strength, time difference of arrival, or maybe also angle of arrival and something like that, are more effective than with respect to one single metric solution. This is because we can get information by both the power in case of the received signal strength and the delay time difference of arrival. And so, by means of well-known equation of the channel state information, we can observe that the mean square error can provide a different, a linear trend, let me say. So, for increasing the SNR, we can observe, of course, a decrease of mean square error, and also at the same time, we can observe that by increasing the number of anchor nodes, or let me say, so the transmitter, the LED, we can observe a decrease of mean square error. So scenarios with very low mean square error can be useful for the previous application that we said before. How this can be reached? These were reached by means of a MIMO system. So MIMO system, in order to have, I'm sorry about that. Let me, okay. So now you should see the, okay, sorry. the full screen. Okay. So we're saying that this was a system with a manual system. More information about the achievable accuracy is provided in this error map for different values of SNR 20 and 40 dB. Of course, in case of higher SNR, we can observe better performances, and here in case of 20 dB we can see that in the middle of the room, so here we can observe the values of mean square error of the estimated error that is smaller, so we are closer to the anchor nodes, so we can better estimate the user position. While in case of higher distances from the anchor nodes, so also near to the walls, this is quite difficult, and so the estimation error is increasing because we are very far from known positions. And also the case of for a row, this constant row 0.66, 0.33 provides better performances with respect of rho equal to 0 or rho equal to 1, that are the extreme cases where only RSS or TDOA works. Okay, so the same consideration can be also applied in case of underwater network. For underwater network, this is the main scenario that we are considering. So this is an hybrid scenario. The main applications, we said, are applications related to monitoring of the waters, the diving tracking, the tracking of divers, and something like that. Okay, we also here reported the wall architecture, also with a radio frequency uplink, a gateway, and an external gateway for a connection to outside. Okay, the situation here is how to track the divers that are moving in this space. In order to do that, we present a finger-based approach that collects information about the waters, the type of waters, and so the channel state information for the overall environment that can be stored and exploited when needed. Of course, information about the current environment, it's a very important aspect, because if we don't have a real match between the database and the real environment, we will see that the performance will get worse. So we need to have a very updated database. Let's see why this is important. So in case of this is the estimation error for a path of a diver that is moving in this environment. And so we can observe that in case that we have a correct match between the database, what we collect, and the real environment, we have a very short error. Okay, so this is, for instance, in case of pure C with a correct database. Let's see on the other side, in case of pure C with wrong database. Here we can observe that the real position is this one, while the estimated position is quite far from the real one. So the algorithm doesn't work effectively. So this is because, for instance, we have a database that doesn't reflect the real environment. So for instance, the water has changed, the water type has changed, there is some rain, there is some more dirty particles and something like that. Okay. Also, the situation, the overall environment is also depending on noise. So in case of there are some additional noise, here we can report the estimated mean square error in case of, for instance, pure C or Arbor C. we can observe in general that there is an increase of the estimated of the mean square error as expected, and but in case of a situation that is dirty, already dirty, let me say. So, for instance, in case of Arbor C, we cannot observe an increase, of the estimation of mean square error as in case of pure C, but the error is already higher also for small values of additional noise. We can, of course, observe that information about the number of anchor nodes about the transmitter can be useful to decrease the mean square error. So, for instance, in case of we have 8 devices that are transmitting, so in this case we can observe that the estimation, the mean square error is around maximum 1.5 meters. While in case of 2 devices, of course, the information, the estimated error is very, very higher. Okay, so how we can support localization services through visible light by means of machine learning. This is very important because machine learning provides more intelligence. It provides a system the ability to learn automatically and improve from the experience without being explicitly programmed. And the methods for localization purpose focus mainly on fingerprint and regression classification methods. So we can extend the fingerprinting approach used in underwater with machine learning aspects. In general, we can observe, we can say that the sensing system can be trained to learn from raw data and analyze the location and the system pattern. So this can be very useful in order to achieve high accuracy system, and also at the same time and not to waste time to and have a training phase that allows to to achieve better performance. I want also to introduce some aspects related to machine learning related to the use of channel charting. Channel charting is a baseband processing approach that involves the application of classical unsupervised dimensionality reduction method that applies to channel state information. So, in order to give a practical example, if we are working in intelligent transportation system, it's important also to have the information about to have the information about how to manage all the information that can be generated by vehicles. So in case, for instance, of data flooding, so the communication from vehicle to infrastructure to vehicle, is important to have an overview of the channel state information coming from different sources, and by means of specific techniques, we can have a dimensionality reduction, so reduce the redundant coefficient that can come from the channel state information, and in this case, as a result, have an information of channel chart. So a graph, a diagram of the channel state, and have an information about how to localize a user. Keep in mind that the channel charting does not provide very high precise accurate localization. So it precise, let me say, a pseudo location, okay? But this can be useful for also for a few applications, few services that are, for instance, that needs privacy. Okay, so it's useful for privacy protection feature, and for instance, in case of contact tracing, in case of pandemics, and so okay, it's important to have high accuracy, but not in all the case, in all the applications. So in a few applications we can also have this kind of pseudo location that can save time and also save privacy. Another aspect that can be useful is the use of device-to-device communication. So it's not only that we should consider only anchor nodes, so transmitter, in order to get information, because in a few environments we don't have always at least 3 devices to get a good estimated position. There are in some cases we can have, for instance, only 2 transmitting devices, and so it is quite difficult to get the accurate estimated localization. In this case, we should rely on the short range communication, device to device short range communication. And so, for instance, in this picture, we can observe that the receiver 1 can get information from receiver 2 to have an estimated position that is in this position and not in this other position here. So keep in mind that not only machine learning to increase the accuracy, but also information about a few situations that does not really need very, very high accuracy, and also information about a cooperation among devices in order to avoid the stuck in environment with high high estimated error. Okay, so in order to conclude this presentation, we overview the needs and the requirements of next generation 6G network. We also observe the visible spectrum that can provide high bandwidth and so can respond to the 6G needs. Localization service will play for sure a relevant role in the next generation network and will require very high accuracy. The solution for this, to match this need, are based on machine learning techniques, and but also at the same time we should consider where to apply machine learning, because not always machine learning can be a response. Okay, so I conclude this presentation. If you have some question, I will be very happy to respond. Thank you.
Okay, Ana Maria, thank you very much for the very nice presentation and overview on the localization aspects of VLC for future 6G networks. So yeah, the presentation now is open for questions. Is there any question?
Well, I have a comment and maybe a question. Ana Maria, thank you very much for very interesting talk. And again, this is the visionary views, isn't it? Yes. Would we'll see on just relying on the visible band? Yeah, the VLC network, just relying on visible band, will, in your opinion, will that be a success, or it will be a downfall? Or does it need to basically get married with something else as well in order to ensure that it's survivor? Yes.
Okay, so well, I didn't mention one important aspect of 6G networks. That is the role of green technology. And so for that, green technology is again of visible light, because of course with respect to radio frequency, visible light wins. And so for sure visible light can be a successful technology. I don't think that we can consider all visible light system. I mean, there will be always the support of other technologies. But this is because, as we saw, there is an overlapping overview of different technologies. And so there are some issues that visible light is still have some problems. So, for instance, mobility is something that it's unfortunately is very difficult. So we should consider the application of visible light not in all the scenarios, but in specific scenario. Yeah.
Do you feel that the future lighting system, if the manufacturers are willing to change, do you think that the future LED lights should also have infrared LEDs in it, part of it? In other words, the light is a hybrid light, both visible LEDs and infrared LED. So therefore, infrared can be used for different scenarios in application.
Yeah, we could consider this kind of device that will switch from VLC to infrared seamlessly. So all optics, it could be also very interesting. That, of course.
Now you have many questions.
Okay,
I
thank you.
appreciate it.
Okay, we have also several questions. Perhaps we have time now for one or two more questions. Please, Hussein, go ahead with your question.
Yeah, hi, can you hear me?
Yeah.
Yeah, Ana Maria, thank you so much for this fascinating presentation. I mean, I really enjoyed it, like your colleagues. My question is about the part of machine learning. Can you, I mean, I suppose we don't have much time, but can you tell us more about it? I mean, it's really fascinating. You said that it needs to learn from raw materials that it has to be trained. I mean, I think you generalized it a little bit. What kind of machine learning are we dealing with? A specific, like for example, microcontroller or language? And when you say learning from raw materials, does this mean you are starting with a specific database and you are then adding to it extra information that you are getting? I mean, in the way, I'm interested in that part very much.
Yeah. The idea is to, this is related to fingerprinting localization. So in the traditional aspect of fingerprinting, you measure the environment, you store all the data, and so you have your database. And then you take this information each time that you want to estimate the position. But this, as we saw, we can have some errors, additional errors, because database cannot reflect. It's not always the same. You know, it's not that this is just a screenshot, a picture of in that time instant the water type is in this way, and so the channel coefficient are those one. So we need to consider a dynamic database collection, storage, and so also update the information that we are getting. So it's not that we have always the same database, but if we are going to get to the database, we make the algorithm learn from this from the coefficient stored in the database, and there will be, for sure, there needs to be updated and to be changed in order to understand how the environment changes itself. So
I see. And then your prediction obviously will be easier because your database has expanded.
Yeah.
Okay. Thank you.
Okay. Well, I'm sorry. I think we are a bit late here. We are on time. But I will ask you, we have two more questions here. But I'll ask the audience to make the questions or the email to Professor Ana Maria, okay? Is that possible?
Yeah, sure. Yeah.
Okay. Thank you once again, Maria. So,
You're welcome. Thank
for
you.
the nice presentation. Yeah, thank you. So let's move on for the next presentation here. The title is Computer Vision Detection and Classification of Emitters for Visible Light Communication. It's a contribution of colleagues here of the University of Santiago. The presentation will be then made by Raul Samonaro Llanes, with the co-authoring of Professor Ismael Soto, Jonathan Pereira Mendonça, Esteban Toledo Mercado, Pablo Adame, and Pablo Adasmi. Please, Vicente, could you run the video? Thank you.
Hi everyone, my name is Raul Zamorano Illanes, and today I'm going to talk about one of the works that we generate on the Center for Multidisciplinary Research in Telecommunication Technologies of the Department of Electrical Engineering in University of Santiago. This work, the title of this work are Computer Vision Detection and Classification of Emitters for Visible Light Communication. So right here we have the table of contents. We are going to start with an introduction for the context of this work, a system diagram with the two stages of this work, the methodology with the math stuff, and the results with some images and videos that we are going to see, and the conclusions. So at first we are going to know that one of the things that matters on VLC communications are the device orientation. So right here we are going to see who the parameters like the azimuth, the elevation angle, and the field of view affects on the communication. We can see right here a table of comparison of positioning systems. Yeah. When we see the indoor positioning system, we can see that a lot of them, most of them, has photodiodes signals like an input. But in these cases, in outdoor positioning system, we can see we have digital cameras and some other type of devices. And in this investigation, we can see we found only one of these works that has number of emitters, like a classification. So what we are proposing are the classification of these emitters. We can see right here that we have an input of a digital camera, and we have a device that has image processing capacity. So we propose it for different applications, for example, indoor communications or vehicular communications. Mining communications are one of the environments that we are proposing. So we can see right here the two phases, the two stages of this work. At the left, we can see that we have an input right here on the dataset generation. We have an input that are the COCO dataset. So all of the images of the COCO dataset are going to segmentate. It has a segmentation, and we are going to obtain the light emitters. So we need to characterize them, and we have a ROI that are the region of interest that we are going to crop and save. So we are going to show it through a user interface to the user. So we are going to tag every ROI, every emitter or possible emitter. We are going to tag them, and we are going to storage them on a CSV file. So with this information, we're going to train a model, and we are going to apply this model on the sequence of the right. We can see we are going to apply the model starting for a video signal. Next to it, a segmentation, a characterization, and with this characterization, we are going to apply the classification model that we generate, and we are going to have the possibility to do response through this analysis. So the methods that we are going to apply consider the frame like a matrix with a lot of pixels or values that we are going to analyze. So one of the first analysis that we are going to apply are the segmentation that are based on the percentile. In this case, the 85 percentile or 90 percentile. We are going to compare this percentile with the value of every pixel, and in this case, we are going to decide between a 1 or a 0. So we are going to have a binarized frame like this, that we can see right here only the emitters or the possible emitters. So in this image that we are going to obtain, we can do some convolution kernels. We can apply some convolution kernels to obtain a better image. In this case, we can see 3 of the kernels that we are going to apply: the mean kernel, the Gaussian kernel, and the Canny kernel. So every ROI, every region of interest, or every emitter that we are going to obtain on every one of these frames are going to be analyzed. In this case, for example, calculating the mean of the variance of this segment. We are going to apply, for example, some other algorithms like Canny, fit rectangle, fit ellipse, or fit polygon. Every one of these algorithms are going to show us some characteristics, some parameters that we are going to save to generate this dataset. So the moments are another features that we are going to storage. These are characteristic in relation with the group of pixels. We have the centroid, for example, that are composed of 4 values of this moment, and we have another moments that are invariants to translations or rotations. So we have a lot of characteristics that we are going to storage in relation of every ROI. So talking about the results, we have right here the segmentation of an image. We can see the different emitters on the right mask. Right here we have the analysis of a video. We can see the segmentation, the schematic segmentation of the emitters in a indoor or an outdoor environment. And we can see right here the application of the different algorithms. We can see in the same video the application of the different algorithms that we are using. So when we start the dataset generation, we can see all the possible emitters that we are going to tag. So the system will show us one by one all the possible emitters, and we are going to tag them. And finally, we have an image with the classification that we realize. So this classification are going to storage. We are going to storage the classification, and we are going to have 75 different variables for train different models. So for our model, we only choose 35 of them, and these 35 characteristics allow us to train a model with an 81.7 accuracy, and only with 5 levels of deep and 11 features, and we can execute the time of execution of this model are only 0.09 seconds for every frame. So we can see right here that in every Git area, only the best performance are on 5 levels of deep. We can see right here the cross-validation test. We can see every combination has the same precision. The confusion matrix of this model. And right here we have the decision tree. We can see that most of the characteristics that this model choose are in relation with the color of the areas and the fit ellipse algorithm. Finally, we have an image that results of the application of our model. We can see the lights that the system are classifying as an emitter, and the another areas that are classified as not emitter. Right here we have a comparison between the different models that we generate. We can see the best model we can generate are the decision tree, has the best accuracy, and in comparison with YOLO, for example, we have a lower time of execution, but this time of execution are only 10 frames per second, with 2 categories and 11 variables obtaining from the frame. So finally, the conclusions, we have that the dataset that we generate will allow the generation of future computer vision applications, for example. Um, the model that we train are only effective on generic image, on Coco dataset image. So for a better performance in another context, we have to train with another dataset. The classification model based on decision trees gave us the highest precision, and the implementation of other like the meters classification model based on the characteristics is applicable on edge devices. The concatenation of the generated model with other computer vision algorithms allowed to reduce the time of execution of this. For example, if we concatenate YOLO with this algorithm, we can only applicate YOLO in array of the image. And future works that we propose are, for example, the integration of the model with a VLC tracking channel, the training of models in different environments, the implementation of the model in different edge devices, the recognition and classification of devices with multiple emitters, and the process of optimization by applying HDL in pink set 1, for example, for a better performance and lower time of execution. So these are going to be all. Here we have the reference that we use on this presentation, and thanks for your attention.
Okay, thank you very much for the presentation, Cesar. Yeah. Let's see. Well, we have questions on this concerning this talk. Is there any question? Yes. Please go ahead, Cesar.
Hello, Raul. I have one small question. I saw that you guys use around 4 to 5 data sets. Could you give us some details of why you chose those data sets?
So at first we need to find a dataset with emitters, with light emitters. So we search that dataset, and I really don't found it. So I start from another type of dataset, and one of them that are I don't know how to say it, but have a lot of type of image are the Coco dataset. So we start on this dataset to generate our dataset of characteristics. Okay. So we process all this Coco dataset image by image. So we generate a program that shows us every image, and we categorize everyone by click, basically.
So
and yes,
from what I'm understanding is that you were not able to find one proper data set for your experiments.
Yes.
So you had to take some images and filter them and make your own data set. Yeah. Is that correct?
Yes, we classified, I think, near to 1,300 images. And in every image, we segmented it through the percentile segmentation, and we got a lot of rows or areas that are possible light emitters, and we tag them everywhere. So
okay. This. Okay. So thanks. It's clear to me now.
Okay. Okay. Raul, thank you. Are there other questions? Edith, I have also one question concerning once you have classified your light sources, no? Do you think it's possible in a future step also to identify the objects to which the light sources are attached? For instance, to identify cars or other mobile devices or so?
Yeah, one of the things that we are proposing on the future works are the application with YOLO. YOLO is an algorithm that recognizes and some type of objects. And if we have a big image, we have a lot of objects. But if this object has lights, for example, we can crop a row of this image and process only this row. So the image is small. So we think that it can be interesting, but it exists the possibility to train a model with the emitter, so we can recognize, for example, one of the studies that we are sitting on the table in the presentation talks about the presence of number of lights. So 3 lights, for example, if the object has 3 lights are one type of object and 2 lights are another type of object. So it's an interesting work that is not in this work, but can be realized.
Okay, thank you. Thank you very much. Is there any other question? So if not, I would like just to thank you all the speakers here participating on this first part of our conference, and also to the participants, and also all the questions that have been placed here to the speakers. And now we move on, but I have to pass on the chair task to my colleague Arun. Okay, Arun, Majundar.
Yeah, I'm here.
Okay, thank you very much. So you can take over.
So can you hear me?
Yes.
Yes, we can hear you.
Yeah, thank you also, Vicent, for helping me with the videos. Okay.
You're welcome. Thank you, Alexandre.
Thank you.
Okay, I will help to Professor Arun with the videos. So, Professor Arun.
Yeah, I'm ready to go.
Okay, so you can start.
Are you going to put the video now?
Can you see the video?
Yeah, I can see. Yeah.
Yes.
We are seeing YouTube. We are seeing YouTube, Diego. Yes.
Yeah.
Okay. My name is Arun Majumdar. I'm calling actually. I'm conducting the conference right now from California in USA, and we have about 6. Let me see. We have about 7 papers, including one keynote paper. So let me go ahead and start. But let me tell you something to the presenters. We'll try to keep the time very tight schedule. So there will be about 10 minutes of talk, and there will be about 2 to maximum 3 questions to be asked and to be answered. And if there is more than 2 or 3 questions, we will just go ahead for the next one. And the questionnaires, the people who want to ask the question, they can submit the questions to the conference in an email or separately. Okay, the first paper is about 10:00 time. It will be network traffic prediction using online sequential extreme learning machine. And I don't see who is going to present the paper, but I assume Francisco Rao will be presenting the paper. So please go ahead and start presenting.
Hello everyone, my name is Francisco Rao. I will present to you the paper network traffic prediction using online sequential stream learning machine. My fellow team members are Ismael Soto, David Zavala, Cesar Azurdia, and Pablo Adasme. Introduction. Recently, with the current COVID-19 pandemic, Internet service operators have been concerned about the high network traffic overload. The increase in Internet traffic was a 15 and 20% in weeks, an amount that is usually spread over several months in a year without COVID-19. This increase will also be driven in the near future by the new 5G mobile network standard. In general, the forecasting network traffic load helps an internet service provider to avoid overloading and optimize the use of resources. The traffic is a time series. The time series consists of a succession of ordinary numerical points of data. The problem of time series is the issue of predicting a future activity from past value and related patterns. Objectives for this paper. 1. The simulation and comparison of two types of neural network to solve the traffic prediction problem for an internet service provider. 2. The application of online sequential stream learning machine for network traffic forecasting not currently seen in similar works. 3. Evaluation of those models with real data from a chill internet service provider. 4. Quickly predict traffic to activate the standby router when their network requires. Theoretical fundamentals. Neural networks have started to be used to predict time series, mainly long-term memory. The calculation of the highest state of the cell is given by the sequence shown in this figure, where it has three gates: input, forget, and output. The structure allows information to be selectively accumulated over time. For this purpose, a series of logic gates and state update equations are added. It's based on optimizing by gradient descent, seeking global minimums. On the other hand, online sequential stream learning machine is a neural network, but its optimized is based on single hidden layer feed-forward neural networks. It's composed of three parts: input, hidden, and output layers. And that allows the algorithm to learn sequential data line part by part using the recursive least square methods. That is very fast. Methodology. First, data will be collected through a monitor that is connected to gateway router from internet service provider. Then data preprocessing will be performed for both models. Then the test will be validated with a validation model. This model is forward chaining, and then the best model will be chosen. Data collection. The different clients are connected by the MPLS network. The internet gateway routers are designed to work in active and standby mode. The internet traffic is the sum of three traffics: international content delivery network and national traffic. This traffic is measured in megabits per second, and this data represents a time series. Data preprocessing. For long-term memory, first step is transforming data into a Sacvlc learning problem. The second step is remove the trend by the data. The third step is we will normalize the observation with the default function hyperbolic tangent with its values between -1 and 1. And the last point is the prediction step is a 1 day. For the online sequential stream learning machine, the first step and the second step is not required in this model. And the normalized observation, the scale recommendation is to standardize the data by subtracting the mean and dividing by the standard deviation. And the prediction step is the same way as the long short-term memory model. Model validation. The data is divided in two parts, training and testing test. To produce a better estimate of model the prediction error, a common approach is to create many training splits and average their errors across all splits. This method is forward chaining. Metrics. We have two metrics, root mean square error, that shows the average division of the predicted values from the target values given by this equation. And the second metric is the time, that is the length of time required to perform a computational model to implement, that is measured in seconds. Simulation and results. The dataset. The dataset is composed of 747 days. That means all traffic pandemic. This traffic is split in three parts that show in this figure. 1 part, 2 part, and 3 part. 186 observations are considered for all split for the testing. First split. We can deduce that the vast performance of the online sequencing stream learning machine is given by the number of lag. It means number of training data, because in figure 11, in the second split, this number is higher than in first split, and the results are better. This does not happen with the long short-term memory. Due is based on gradient descent, optimized according to the data series or batch given to the network, and looks for an optimum. Remember that in this model, we have a number of epochs. In the tree split, which is when we have the most lags, we can see that online sequencing stream learning machine performs better, but fails to predict the traffic peaks, which is shown in this figure, is compared to long short-term memory. In this style, we can visualize that the best average root mean square error is obtained by the long short-term memory. But we visualize that the data of the second split and the third split, online sequential stream learning machine has a slight improvement. The reason is the increment number the training data. On the other hand, the speed of online sequential stream learning machine is extremely higher than long short-term memory. The main difference of online sequential stream learning machine is that does not run the slot learning algorithms based on gradual descent, but use the Moore-Penrose pseudo inverse. Conclusions. This paper investigates the deep learning model for traffic log prediction in a real internet service provider. Experimental results confirm that both models are applicable to real data and real networks. The advantage of the online sequential stream learning machine is the training speed. Science is faster than the long-term memory. The results show that the online sequential stream learning machine outperforms a long-term memory in terms of a computational cost by a factor the 2,300, and in terms of network prediction, online sequential stream learning machine effectively competes with long-term memory. And finally, the application of the online sequential stream learning machine model can be implemented in the following scenario. Two routers are available, and in this situation, then one router cannot support all the traffic load. The network must quickly predict the traffic load if should automatically switch in and start standby to active scheme. Thank you very much.
Okay, thank you. We have time for a couple of questions. So, anybody has any question? So, no question, right?
There is one from Fabian.
Okay.
Thank you very much for the presentation. The only question that I have is how you will use this model, because you have a very good prediction, but with this prediction, what are you planning to do, or which algorithm, or what are you planning to do with this prediction of the data rate?
Hi. I think the prediction is for many things. One thing is about how to predict the energy of it could be the situation that you can see several nodes, and these nodes you can turn on or turn off. It depends on the traffic in this situation. If for that reason this all this that simulations could be for 1 second for this prediction, or for all the traffic is very short. This is one applicable for this model.
So Fabian, did you understand the answer?
Yeah, thank you very much.
Okay, we have one more question. We have a time for one more.
Ismael.
Yes. Yes, Professor Aaron, yes. Well, as you know, we are involved in the paper. And rather than present a question, I would like to use it to support the explanation that Francesco did. It's supposed that in the near future, we will go for green energy. And if we have a higher consumption of the ISP network provider, means that we have to connect new solar panels. And then we need to predict for short and long-term use of the internet provider. Because if we use traditional generators, yes, they have more inertial and then it means that they are more time delay. But when we have a battery and green solar panels or wind, yes, we need a quick response from the internet provider in order to reply more energy and try to predict that, especially on the long term. And long term prediction is really a issue. With Francisco, we've been working in a short term, medium term, but long term, as is so difficult. I remember that one of our students, Raúl Carrasco, that maybe is connected, we tried to predict the copper price, yes, and that isn't related, you see, with the production, yes, of the copper. And I remember that we went to, at that time, we were able to go to London to present our paper, and it was a guy asking that why we are trying to predict using and I'm presenting result for short term, because it's so difficult. Because it's so difficult to predict. Suppose the variation of the copper price. And in the case of ISP, it's exactly the same. So at the moment we are getting result for short and medium, but not for long. Yes, at least we have 1 day. Yes, isn't it, Francisco? 1 day for long term prediction. Yes, but long term prediction, 1 day long term prediction is enough to prepare. You see the electric power system. You see from the solar panel. That's my support to the Francisco response. Thank you. Are you happy with that, Fabian?
Yeah, thank you very much.
Thank you.
Okay, I have one silly question. Actually, I forgot to ask.
those are the worst. Huh?
Is this neural networks what you are talking about with all that? It's very complex, very interesting. Probably can be real. Can you make it an optics chips of a neural network? In other words, can you make a very small optic chip which will do the same, operate like a neural network, and can be stick it on some devices, optical devices?
Yes, of course. Can I respond that, Francisco, or do you want to respond?
What do you prefer?
Yeah. He's saying if we can do that in optical devices.
And you can make an optic chip to do that job, right?
Of course. Can I respond that? Yes. Of course we can do that in the near future, and there are some there are some prototype you see in some papers where they try to do that. But with my colleague David and Cesar, we have discovered that the extreme machine learning is one of the fastest network that we have at the moment.
Quasi real time.
Almost real time, yes. And for that reason, we've been applying in vehicle-to-vehicle communication and many other things. Yes, and especially in this case for production or for prediction. Before the training of a rumor architecture or deep neural network was very time consuming, and the response not always was as fast as we want. But when David, brought the LAM network, we start to review all our projects, and with Francisco we have the opportunity to prove in real data We don't have to contract the data set as in the case of Raul. In this case, we took real data from the ISP provider. And then we are starting to predict for short or short-time period. And well, but we are not very successful for long period because it's so difficult. No? But one day is enough. Thank you. Thank you.
Okay, thank you. We move on to the next talk, please. So, where is the video?
Diego will put that.
Okay, this title of this talk is Bit Error Rate Analysis for OFDM Schemes Applied to Underground Mining VLC Systems. And they are from University of Chile, UDLA, and University of Technological Metropolitana, STIC, AMSUD. I don't know how I pronounce correctly or not. And again, I am assuming the talk will be given by Pablo Palacios. They should have written that who is going to give the talk. I don't have that information. So let us move on, please.
Hello, my name is Pablo Palacios, and today I'm going to explain about our research bit error rate analysis for OFDM schemes applied to underground mining visible light communication system. First, I'm going to introduce the main concepts about this topic. After that, I'm going to explain the problem definition. Then I'm going to present the underground mining VLC system model and the OFDM schemes applied in the research. After that, I'm going to present the simulation results. And finally, the most important conclusions and the references are presented. Underground mining environment is one of the most dangerous to work in for its work features. To mitigate these issues, complementary alternatives to common radio frequency-based technologies are present in the literature, such as visible light communications system. An important feature of visible light systems is specifically in underground mining VLC schemes is a high data rate to meet the technical needs of mining application. Therefore, techniques based on orthogonal frequency division multiplexing have been proposed in the state of the art. But what is the problem? The problem is that OFDM signals designed for visible light communication system must comply with the intensity modulation and direct detection. Therefore, we need signals real and non-negative. In this paper, the performance of the three techniques, ACO OFDM, DCO OFDM, and ADO OFDM are evaluated and compared. First, about the underground mining VLC system model, we have three principal components. Light of sight, as we can see in the expression 1, the non-light of sight, and the scattering channel gate. The three components depends on the radiation angle, the incidence angle, the tilt and rotation angles, the shadowing, and the third component depends on the scattering particles. Finally, the overall underground mine VLC channel gain is the sum of the loss, non-loss, and scattering components, as we can see in the expression 4. The signal received by the photodiode is composed of the channel gain, the overall channel gain, with the X signal and the thermal and shock noises. As we can represent these noises with the N component. First, before implement the OFDM schemes, we need transport the signal, the X signal, using the Hermitian symmetry, as we can see the expressions 6. The disadvantage of this technique is that the spectral efficiency is reduced by 50%. This is the first step for all the OFDM VLC schemes. The first scheme is the DCO OFDM scheme, as we can see in the block diagram of the presentation. After the signal is processed to obtain the Hermitian symmetry, the output is serialized using a parallel serial block. Then a cyclic prefix is added and converted from digital to analog using a digital analog converter. Finally, the signal passed to a low pass filter, and the output signal X is transmitted for the optical channel. OFDM signals are widely known to have a high peak-to-hour power rate. Therefore, it's necessary that a large I sub DC in order to remaining negative peaks. Finally, in the signal received by the optical receiver, as we can see in the diagram block, is converted to electrical, and in this conversion appear the shock and thermal noises, typical in underground mining VLC system. After conversion, the signal processing is similar to that performed by the atypical OFDM receiver. The second scheme is the ACO OFDM scheme. In this scheme, the odd subcarriers carry the data, while the even subcarriers form a biased signal to make the signal positive. Therefore, signal X, as we can see in the expression 10, is present. As we can see the block diagram of the ACO FDN scheme, in this case, the signal transmission of the optical signal until obtaining X tip is similar to the DCO OFDM. Consequently, XT signal is clipped to 0, obtaining the ACO signal. This clipping does not produce information loss because the signal is antisymmetric and the clipping distortion only found on the even carriers. In this figure, we can see the effect to clipping signal to 0. The last scheme is the ADO-OFDN scheme. This technique combines ACO-OFDN transmission scheme on odd subcarriers and DCO-OFDN on even subcarriers. On the other hand, In the receiver, the OBSU carriers are demodulated with a traditional ACO OFDM receiver. However, an interference cancellation process is performed first to demodulate the odd subcarriers. The ADO OFDM transmitter and receiver, as showed in the presentation. Numerical results of the VLC system performance evaluated with the specific underground mine VLC channel model are presented. The results were obtained through computer simulations, where the 3 schemes are applied and compared using different QAM modulations in the range between 4 QAM and 16 QAM. The appropriate evaluation metric for comparisons and analysis is the BER. The BER curves for the 3 OFDM schemes analyzed with modulations from 4 and 16 QNA, and considering with the 3 principal components of the underground mine VLC channel. As we can see in the curves, if we compare the curves, the ACO OFDM scheme is better compared with the other OFDM scheme. Its performance is due to the fact that the ACO OFDM scheme only uses half of its subcarrier to transmit data. Therefore, its bit rate is half compared to the other schemes. The most important conclusions are presented. First, we will evaluate underground mine VLC systems with 3 OFDM schemes for N QNA modulations ranging between 4 and 16 QNA. The ACO OFDM schemes, besides being a simple solution for signal dispersion, has a greater optical capacity. On the other hand, the performance of the ACO OFDM depends on the bias current that produces a clipping noise, which limits the performance. In the ADO OFDM scheme, the bias current of the DCO OFDM section affects the ACO OFDM section. This effect produces a low performance. Finally, non-lossless scattering components produce multiple, which generate phase and amplitude shifts of the optical signal. Most important references used in this research are shown. Thanks for your attention.
Thank you very much. A very interesting paper, and I like to ask the audience if anybody has a question.
Yes, I do have a question, Professor Aaron. May I ask it?
Okay, go ahead, please.
Okay. I just wonder if you have considered in your model the nonlinear response of the LID for estimating the response of the OFDM.
Where is the presenter?
Hi. About your question, in this model, we consider ideal LED model for the baseline sperm. In this case, we don't consider no linearity effect for this moment, but for future research, we need to consider a real model. And in this case, we consider all the no linearities effects.
Okay, thanks. I think it's very interesting and important to consider this because the OFDM performance will change according to the LID response. No? So
yes, that's totally agree with you.
Yeah. Okay. Okay, thank you.
Thanks for your
Just
question.
one observation, Professor. I'm also co-author of the manuscript, and what you mentioned is really important because this will also affect the PAPR of the system, which is something that really affects OFDM schemes. So thanks for the indication, and something will be considered as future work.
Okay.
May I ask a question? I have a physics-oriented question, very basic question. Two questions. One is what kind of wavelength range for the visible light you are considering, and that will lead to my real question is that about the scattering part. So what are the sources of scattering, where the particles are coming from, what kind of scattering? Could you tell me a little bit about wavelength and the scattering, the origin of scattering?
About the second question, I can respond this question. The scattering model used in this work is a unified disk scattering model around the minor, and this model consider those particles in just a circle area, and the scattering is the signal is the signal is out about the LED, produce a scattering effect when impact with the dust particle, and then reach the photodiode. This is the basic model about the scatter.
What is the wavelength range? Because wavelength has to do with the scattering sizes, by the way. So can you tell me a little bit what kind of wavelength range you are talking about? And I still didn't understand what the particles are. Which particles, in the air or in the mine or where?
We use two models, Maye scattering and Rayleigh scattering, and we work in the wavelength range about the PLC system currently work is general, is not a specific wavelength range, but just all the range of wavelength. In this case, don't use a specific wavelength.
Okay, so the misscattering or the other, they can be about the size of the particle sizes can be a little bit more than the wavelength or so probably. And I think that should work. But where are can you tell me which particle we are talking about? Where are they? Where is the source of the particles? I still wanted to visualize that. Where are which particle?
Okay, just I will complement Pablo's explanation. Most of this analysis, we have been doing it for underground mining. So there is a lot of dust particles in the mine. So that's what we're trying to model with this scattering. It's basically dust.
So that's my problem, that if you have a underground mining, then the scattering, those particles are not spherical at all, probably. Probably they are non-spherical, and the misscattering, does it hold, or Anyway, we don't want to. I don't want to waste your time at this point.
But what you're saying is true. This was the initial approach, and it's part of ongoing work, especially by Pablo. We're trying to come up with better models for the scattering, specifically for the underground mine, because this was just a two-dimensional.
Scattering is a very complicated problem.
It is.
Yes, sure.
It has been, solving for hundreds of years, but especially the non-spherical particles, because those are, anyway, those are complex problems. That is not the main issue of the talk, but I enjoyed the talk. And can you move on to the next talk, please?
Okay. Thanks for your observation.
So can I have the video for the next talk?
Okay, the next talk is a keynote speaker, Professor.
Okay, so let me see. I have a just 1 second. Okay, the next talk is this is a keynote speaker, Dr. Rui Wang, and I have his biography. I'm going to read just a few sentences about Dr. Wang. So Rui Wang received the PhD from the Shanghai Jiao Tong University in China in 2013. And from there, he was a visiting PhD student at the Department of Electrical Engineering, University of California at Riverside. And I believe I have met him. I don't know, because at that time I was still in California, and then then I had another colleague. He was teaching at the University UC Riverside, so I might have met, but even if I have not, but I am familiar with the department. And then from there, he from 2013 to 2014 of October, he was with the Institute of Network Coding, the Chinese University of Hong Kong, as a postdoctoral research associate. And from October 2014 to December 2016, he was with the College of Electronics and Information Engineering, Tong Jai University, as an assistant professor. And now he's currently an associate professor, and congratulations for that. So Dr. Wang received a lot of rewards. One of them is Shanghai Excellent Doctoral Degree Dissertation Award 2015. Received the ACM Shanghai Rising Star Nomination Award 2016. And I don't know that ACM might stand for, is that American? I don't know, but ACM Shanghai Rising Star nomination. And he has published a lot of papers, more than 60 articles, and his main research interest is MIMO technology, network coding, and OFDM, as he is an associate editor of IEEE Access and an editor of the IEEE Wireless Communication Letters. So let me present Dr. Rui Wang. You will all enjoy the very interesting talk, and we have a lot of time. So thank you, Dr. Wang, for presenting us, and please start your presentation.
Morning, everyone. I'm honored to have an opportunity to be here to present our latest research results. And I also would like to thank the committee for the invitation. And the topic of my presentation is the location information assisted beamforming design for reconfigurable intelligent surface edit community systems. And I am Rui Wang from Tongji University, Shanghai, China. And this is the outline of this presentation. In the first part, I will give the background and the motivation of this presentation. And the second part, I'll give the system model and the main work. And in the third part, I will give the discussion and the future work of this presentation. The first part. 5G has entered the commercial application stage by using mainly advanced technologies such as millimeter wave massive MIMO. So the performance of the 5G has been greatly improved compared to the 4G. But 5G also have some disadvantages, such as 5G face severe pass loss and higher energy efficiency and higher deployment cost. So then in the future 6G, so we actually want to achieve the higher spectral efficiency and low energy consumption and lower deployment cost by using some new communication paradigm. So in this situation, so reconfigurable intelligent surface, also called RIS technique, is our most promising candidate. So the RIS technique can achieve a near passive communication and has a lower energy consumption and low cost, and and is reconfigurable and easy to deploy. So RIS can make the wireless communication environment smart, and RIS has been considered as the most promising candidate technologies in the future 6G communications. So actually, so the RIS has been widely studied recently from different aspects, such as the optimizations, the performance evaluations, and the designs. For the RIS-assisted communication systems, the passive beamforming design is very important. Passive beamforming design actually just adjusts the reflection elements such that the RIS can improve the reflecting, the quality of the reflecting. But here the challenging problem is that the passive beamforming design at the RIS require the channel state information. And because the number of the reflection elements at the RIS is very large, so the CSI acquisition technique is very challenging. So the challenging comes from several aspects. The first one is that we require the long channel training process to estimate the channel. So the training process overhead for the RIS system is very high. And the second aspect is that if the RIS equipment is general passive equipment, it cannot it cannot estimate the channel itself. If the channel estimated by the base station, so the feedback, the CSI from the base station to the RIS will require high extra communication overhead. In this case, so in this study, we want to solve this problem. We just use the location information to acquire the CSI. So we consider the RIS assistant communication in the millimeter wave frequency band. So in this case, actually, the channel between the base station and the RIS, or between the channel between the RIS and the mobile users, actually highly depends on the location information. In this case, so the idea of this study is to use location information to reconstruct the channel for the beamforming design. So in this study, we consider this kind of channel model. We assume that the direct link transmission between the base station and the mobile user is blocked by this building. So the transmission between the base station and the mobile user has to be assisted by the race. So here we assume that the location information of the base station of the race and the mobile user are long in pair. In this case, we can use this location information to reconstruct the channel, and then we use this channel information for the passive beamforming design. And this is the overall idea of this study. But here we face some challenging problem. That because the location information of the mobile user is obtained by using the GPS systems. And this location may have errors. So in this case, the reconstructs the channel will also have errors. So in the beamforming design, we have to consider this error to avoid the performance degradations. So we require the robust beamforming design in this study. So this is the contribution of this work. So the first contribution is that we construct the 3D race added millimeter wave communication systems, and we establish the relationship between the location information and the channels. And the second contribution is that we derive the approximate channel error bound based on the user location error bound. And the third contribution is that we formulate a worst-case robust beamforming design problem. And we propose a low complexity iterative algorithm which converge faster than the existing methods. And in the part 2, I will introduce the system model and the main work. And this is the channel model of the considered systems. And here, the HBR deloads the channels between this base station and the race. And the HRM just deloads the channels between the race and the mobile users. We can see here the channels contains two terms, and the first term actually is the term of the line of sight, and the second term is the long line of sight term. So here the line of sight term actually depending on the location informations. Actually, so here the channels can be represented like this. Here the parameter, so this path loss parameter and this parameter actually depending on the location information given in this form. So this is received signal model. This YT the received signal at the mobile users, and here this W is the beamformer used at the base station, and this diagonal matrix phase shifter. This is the diagonal phase shifter matrix used at the race, and here we assume that the magnitude of the reflection elements are equals to 1. But here for the phase, we consider 3 different cases. In the first case, we assume that the phase can be changed over the range from 0 to 2 pi. And in the second case, we just consider the phase can only be chosen from a given interval. And in the third case, we assume that the phase can only be chosen from a discrete set. This is the location error model and the channel error model. So here we assume that the P just deloads the location information of the mobile user. And this P hat is actually the inaccurate location information provided by the GPS system. And this delta P is the location arrow, and this arrow is bound like this. And using this location information, we want to reconstruct the channel. But here, because we only know this inaccurate location information, we can only reconstruct this edge hat. So here, we want to determine this channel arrow such that we can design the robust beamforming design. So this channel arrow can be given like this. It includes two terms, and the first term this term is determined by the location arrow, and this term actually determined by the long line of that term. So this is the problem we formulated for the beamforming design. And our objective function is to maximize the minimum received power at the mobile user. And the first constraint is the power constraint at the base station. And the second constraint is the channel arrow bounds. But here, this bounds is unknown, and in this study, the key point of this study is just to derive this arrow bound. And the third constraint is just the constraint for the phase shifter. So the first key point is just to derive this channel arrow bound by using the location arrow bounds. By using some approximations, we can obtain the upper bound of these channel arrows given like this. So here we can find that the upper bounds contains three terms, and the first term actually depends on the location arrow, and this is the term determined by the inaccurate reconstructed channels, and this is the term introduced by the long line of set terms. Here the key point is just to derive this term. So by using the geometric relationship between the location and the channel, we can represent this arrow in this form. So here the nonlinear functions omega actually is the nonlinear functions of the location informations and the arrow. Here the key point is to derive the upper bound for these omega functions. So here we have these results. And in this lemma, we find that the upper bounds of these omega functions can be obtained by solving this optimization problem. Okay, this is the convex optimization problem. So by solving this optimization problem, we finally obtain the channel arrow bounds given in this form. Okay, so here I give some simulation results to check the tightness of the proposed theoretical channel arrow bounds. So here, the red curve actually is the results of the actually channel arrow bounds, and here the blue curve actually is the theoretical channel arrow obtained by our proposed analysis. So we can find that the proposed theoretical channel arrow bounds fit well with the actually channel arrows. Actually, here we can find with the increase of the number of the reflection elements, so the arrows become higher. Also, here we can find that the theoretical channel arrow bounds it's also a higher upper bounds with the actually channel arrows. So in these three figures, we just illustrate the gap between the actually channel arrows and the the derived theoretical channel errors for different distance between the race and the mobile users. So here we can find that when the distance between the race and the mobile user increase, the gap between the derived theoretical channel error bound and the actual channel error bounds decrease. So now with the derived error bounds, we just perform the robust beamforming design, and this is the overall robust beamforming design problem. So here we can see, here we have two variables. The W is the beamformer used at the base station, and the theta is the phase shifter variable, diagonal. This is diagonal matrix. So for the beamformer used at base station, we can find that the optimal beamformer at the base station can be given in this form. Actually, this is the matched filter form. So by substitute this base station beamformer into the problem, so we can reduce this original optimization problem in this form. For this optimization problem, we propose an iterative algorithm to obtain the passive beamformer at the race. So in this iterative algorithm, we have an inner minimization problem and an outer maximization problem. And in the inner maximization problem, we want to find the worst case delta H. And in the outer maximization problem, we just find the passive beamformer used at the race. And for the inner optimization problem, we can find this is a convex optimization problem. And by using the KKT condition, we can derive the closed form, the solution, which is given in this form. So here we can find that here we have an unknown parameter mu, and this mu can be determined by using the bisection search technique. And in the outer optimization problem, we want to find a phase shifter passive beamformer to maximize the received power at the mobile user. So here, by using some transformations, we can transform this optimization in this form. Here we can find that both the objective function and the first constraint are actually has a quadratic form with respect to the theta. Here the theta is the passive beamformer vector, which includes the diagonal elements of this big theta. Now, to solve this problem, we consider different phase conditions. If the phase constraints is given in this form, we just propose to use this SDR algorithm to solve this passive beamformer. But if the phase is given in this given interval, or if the phase is only choose from the discrete set, we propose a modified branch and bound algorithm. This is the BNB algorithm to solve this problem. So BNB algorithm can find the approximate optimal solution. This is the overall the beamforming design algorithm of this study. And here we also compare the complexity of the proposed algorithm with the two benchmarks. So here the first benchmark is the non-robust beamforming design, and the second benchmark is the robust beamforming design proposed in these two papers. So here we can find that for the robust beamforming design, actually the complexity depends on the required number of iterations. And for each iteration, we can find that the complexity of the proposed SDR algorithm is smaller than the benchmark 2. But the proposed complexity of the BNB is higher than the benchmark 2. But from the simulation, we can find that the required number of iterations of the proposed algorithm is smaller than the benchmark 2. So here, this is a simulation comparisons. So here, from these two figures, we have three methods. The black curves are just the performance of non-robust beamforming design. It had the worst performance. And here the red is the performance obtained by the benchmark 2. And here the blue curves is the performance of the proposed algorithms. So here we find that if we only have 3 iterations, we can find that the proposed algorithm greatly outperform than the benchmark 2. And if the benchmark 2 has 10 iterations, the performance will approach the proposed algorithm with 3 iterations. Here, this is a comparison of the convergence rates of the proposed algorithm. And here, so these two curves are actually the convergence rate of the proposed beamforming design. And this red curve actually the convergence behavior of the benchmark 2. Here we can find that the proposed algorithm converge very faster than the benchmark 2. Now I give the discussion of this study and provide some future works. So the advantage of this study is that we proposed a communication design scheme for the race-assisted communication systems, which does not require the channel training process. And the proposed design is robust to the location error, and the proposed passive beamforming design algorithm outperformed the non-robust approach and outperformed existing robust beamforming design. And for this study, we also have some limitations. The first limitation is that actually the beamforming design are actually based on the upper bounds. So because this channel upper bounds is derived by using the GPS upper bounds. So in the future work, actually we can directly include the location error in the optimization upper bounds. We may obtain the improved performance. The second limitation is that in the millimeter wave channel, actually the channel is sparse. So we can use this sparsity to reduce the complexity of the proposed algorithms. And the third limitation is that the GPS signal is very weak in the indoor environments. So in the future work, we can combine some other location techniques in the indoor environments. Thank you for your listening.
Thank you, Dr. Wang, for the nice presentation. And we have a few more minutes for the audience to ask a few questions. So I will ask the audience if anybody has any question. Okay, Fabian, ask your question.
Thank you very much. I do have one question regarding the indoor scenarios and the positioning that positional algorithms and also intelligent reflector surfaces. And it's basically how it would be convenient to move for indoor scenarios, for example, using IRS with the VLC communications, like smart mirrors or devices like those ones.
Okay, so thank you for your question. So, so for our study, so we use the location information to reconstruct the channel for the passive beamforming design for the race system. But if in the indoor environment, so we may don't have the GPS signal. So in this situation, actually, so our system, our proposed scheme cannot work. But if we have some other systems which can provide the location informations, so we can also use this location information for the passive beamforming design. For example, in the indoor environment, we can use the Wi-Fi technique to provide the location information, or UWB or some other system. If the system can provide us the location information, so we can use this location information to reconstruct the channel, and then we use this channel information for the passive beamforming design.
Thank you very much for your presentation.
Okay, thank you. Pablo, that's your chance now to ask the question.
Okay, thank you very much. I was wondering if, or I want to ask you if you have thought about applying maybe some stochastic programming approach instead of robust optimization. Robust optimizations always lead to very conservative solutions, as you mentioned in your presentation. So I was wondering maybe if some stochastic programming approach is valid for your experiments. And also, I was wondering how many branch and bound nodes did you obtain when solving your problem to optimality in discrete manner?
So sorry. So the questions about the branch and bound algorithm, right?
Yeah. I was wondering how many branching nodes did you obtain in your numerical result when applying this exact algorithm based on branch and bound?
Branch and bound loads. Maybe I don't know. See, actually, branch and loads is one kind of algorithm to find a solution for a non-convex optimization problem.
Yeah.
Okay. This is just one optimization tool to solve a non-convex optimization problem. So in our study, we use this branch and bound to solve our passive beamforming design problem when the phase constraint is not in the range over from the 0 to 2 pi. Because when the constraints when the phase constraint is not in the range from the 0 to 2 pi, so this the passive beamforming design problem is very challenging. Okay, so actually existing optimization solutions cannot be used here. So in this case, we just propose to use the bound and branch algorithm. Okay, this is a powerful algorithm to solve the non-convex optimization problem. But the disadvantage of this algorithm is that the complexity is very high.
Yeah.
So yeah, this algorithm has a higher complexity to obtain the good solutions. Yeah.
Okay.
Thank you.
Okay.
Thank you.
Lindsay, you can ask your question now.
Professor Wang, how do you design beamforming in the case of the mobile user moving fast relative to the base station?
Okay, this is a very interesting question. Yeah, when the mobile user moving very fast, we have some other challenging problem. If the one most important challenging problem is that when mobile user change faster, the channel will also change quickly. So in this case, so in our system, in our communication system, so we may have we cannot get the instantaneous channel. Okay, instantaneous channel cannot be obtained for the beamforming design. Okay, this is because when the channel change very fast, so the we may have time delay to obtain the instantaneous channel. Okay, in this case, we actually we have students to start this point. So we propose to use the reinforcement learning to solve this problem, because we when we use the reinforcement learning, we can use the old channel information to predict the instantaneous channel. Okay, so although we cannot obtain the instantaneous channel, but we can use the old information to predict this channel, and then we use this predict channel to perform the passive beamforming design. So we find that we can get the good performance. So when we use the reinforcement learning methods.
Oh, I see. Thank you. Thank you.
Okay, that's your time to ask the question.
Okay, Professor Wang, I have a question. In the experiment, the sparse geometric millimeter wave channel model is considered, but in most scenarios, it should be a general fit model. Will it lose its generality?
Yes. So in this study, our methods cannot be used for a general case, but because the reason we consider the millimeter waves channel frequency band is because that's the line of that term dominates the channel. Okay, so because the line of that term highly depends on the location information. Okay, so if the system operates in the low frequency band, the long line of that term will be large compared to the line of that term. So in this case, so the channel cannot be reconstructed by the location information. Okay, so in this case, because the reconstructed channel does not match with the real channel, so I propose scheme cannot work very well. Okay. So
okay, thank you.
Okay.
I know it.
Is there any other question from the audience? If not, I thank you very much, Professor Wang, for the nice presentation. I hope a lot of participants learned a lot from your presentations, and thank you for joining. Okay, now we go to our regular session. Mode division multiplexing based hybrid on PON FSO system for last mile connectivity. The paper will be presented by Harjivan Singh and with other authors Nitin Mittal and Rajan Miglani, and myself is one of the authors. Okay, thank you, and please start your presentation.
First of all, I would like to extend my warm greetings to the Honorable Conference Chair, delegates, and organizers of Sacvlc 2021. In addition to this, I also welcome my fellow researchers who are contributing and participating in Sacvlc 2021. The title of our paper is a Mood Vision Multiplexing Based Hybrid PON FSO System for Last Mile Connectivity. My name is Harjeevan Singh and I am presenting this work. The co-authors of this work are Professor Nitin Mittal, Professor Rajan Menglani, and Professor Arun K. Majumdar. First, I would like to give a brief outline of our presentation. I will start with a discussion of passive optical network, mood vision multiplexing, and free space optical communication, followed by objectives and proposed system design of this work. And then at the end, we'll discuss results, conclusions, applications, and future work of our work. Let us discuss passive optical network first. Since we know that passive optical network is basically a fiber optic network utilizing point to multi-point topology, and it uses optical splitter to split high-speed data stream from a single transmission point to multiple end users. Apart from this, passive optical network is also capable of offering huge bandwidth, very high data rates, high number of user connectivity, cost-effective solution, and it also offers flexible and scalable system design. And nowadays, in order to support new services having requirement of high data rate over longer distances, passive optical network is a very potential candidate to support communication and multimedia applications requiring high-speed connectivity. Passive optical network, they are becoming commercially viable, and the deployment across the globe has been reported as well. Now, coming to mode vision multiplexing. In mode vision multiplexing, basically, we are sending multiple modes simultaneously. So we are using the concept of mode vision multiplexing for a proposed system design by launching various modes simultaneously in order to increase or enhance the aggregate bandwidth, to reduce the power consumption of system, to enable easy upgrades in the system so that we can remove the bottleneck of last mile access network. We are using Lagrangian modes in this work, and we are transmitting LG00, 01, 10, and 11 mode simultaneously. The amplitude profile of LG modes can be mathematically represented by this equation, where R and phi, they represent the cylindrical coordinates, W0 is the spot size, L subscript Mn, it represents the Lagrange polynomial, where M and N represent the radial and angular distribution modes. Lambda is the wavelength, R0 is the radius of curvature. Now, sometimes it is not feasible to deploy optical fiber network. For example, in case of difficult terrain, due to some geographical constraints, the ground is not that good for deployment of optical fibers. Or sometimes due to high installation cost or high installation time of fiber optical network, we can use some other technology. We can replace some portion of our fiber network with some alternative technology. So free space optical link is one of the most viable solution in this type of scenario, which offers us high speed optical connectivity. But in this case, we are sending data through the atmospheric channel. So we can integrate passive optical network with free space optical links in order to provide high speed connectivity for end users. So here, this is a hybrid PON FSO system design where central office connected with fiber network is representing our passive optical network, and then we are shifting to the free space optical link where we are sending data through free space, and then we can ensure the connectivity of last mile users via high speed data rate. So this is how we can collaborate passive optical network and free space optical link to propose a hybrid system design for ensuring the high speed connectivity of end users. Now let us come to objectives now. Due to sudden explosion of high-speed internet applications, 8K, 4K video broadcasting, IoT-based applications, 4G, 5G mobile networks, the current network infrastructure is not capable of providing high-speed connectivity to the last mile users. So there is a need to find some alternate technology in order to ensure the high-speed connectivity of end users. So first we are proposing a high-speed hybrid PON FSO system for ensuring the last mile connectivity, and that too at high data rates. And then we are further investigating the performance of proposed system design for various LG modes, which are LG 00, 01, 10, and 11. So this is a proposed hybrid PON FOS network for our system design, where 4 different modes have been generated, which are LG 00, 01, 10, and 11. We can generate these modes via various techniques, like we can use spiral face plates, we can use computer generated holograms in order to generate these modes. These are then multiplexed by a spatial multiplexer, and then they are transmitted on fiber network. The fiber network in our work is representing a fiber network having attenuation of 0.2 decibel per kilometer, and then we transmit the data through optical wireless mode. So we are using the free space optical transceivers for sending and receiving the signals, and then they are demultiplexed by spatial demultiplexer and then forwarded to appropriate mode selectors, which select the appropriate mode like LG 00, 01, 10, and 11. These are further sent to the spatial optical receivers, and then the data is delivered to the end users. So these are some of the simulation parameters we have used for our work. You can have a look over them. Let us discuss the results now. So these are the generated modes, and here we are representing LG 00, 01, 10, and 11. So LG subscript MN. Now M and N, they represent specific things. Like M is basically representing the number of concentric rings of intensity. So in case M is 0 here, we can see that we are having only a single node. On the other hand, N represents the angularly distributed modes. So as the value of N is raised from 0 to 1, we can see the angular distributed modes in figure B. Similarly, if we increase the value of M from 0 to 1, we can see that now we are having multiple rings of intensity. So as we increase the value of M, the pattern, it has now multi-ring shape. Similarly, on the right hand side in D part, we can see the pattern for N equals to 1. So angular distributed modes corresponding to value of M equal to 1 can be visualized here. Now, we are transmitting the multiplex modes on fiber-based network and free space optical link. In our work, we have considered the fiber-based network having 2 lengths. One length is 10 km, second length is 20 km. Free space optical link has been shown here, which was discussed earlier as well. So now, basically, the fiber length has been changed. It is 10 km and 20 km. So first parameter here is the SNR. Similar to my search for a link to 500 meter, we have illustrated here for various modes, and we can see that LG mode is performing very well as compared to 01, 10, and 11 mode. The SNR corresponding to link range of 500 meter is around 29 dB. Similarly, the SNR in case of LG11 mode is around 12 dB. Hence, we can see that LG00 mode is performing very well as compared to other modes. Similarly, for fiber length of 20 km, again we can see that LG00 mode is performing exceptionally well as compared to 01, 10, and 11. Next is the bit error rate. Here again we can see that the BER of desired system in case of fiber length of 10 km and 20 km has been showcased, and we can see that for a link range of 500 meter, LG11 mode is giving us degraded BER performance, which is clearly visible from the eye pattern as well. The lesser opening of eye diagram indicates the high degradation of data signal. On the other hand, if we see LG00 mode is performing very well. The BER performance is also best in case of LG00 mode, and we can see this from the eye pattern as well. The clear eye opening indicates very lesser degradation of transmitted data. Same for fiber length of 20 km, we can again have the same result. Now we are finding the maximum achievable FSO link ranges. The target BER is 10:-9, and we can see that for fiber length of 10 fiber length of 10 km and target BER of 10:-9, LG00 mode is giving us maximum link range of 950 meters. LG01, 10, 11 are giving us lesser maximum achievable link distances. Similarly, for fiber length of 20 km, again we can see the maximum achievable distance in case of LG00 is 710 meters, which is high as compared to the other modes. So this is again a Q factor comparison of two systems. In one system, we are transmitting the modes And the other system, we are having the transmission without any modes. So we can see that for a link range of 700 meters, the design system is giving us very good results. The Q factor in case of LG00, 01, 10 and 11 is quite high as compared to the transmission without any spatial modes. But beyond 700 meters, we can see that the system having no spatial mode is performing better as compared to the system having spatial modes. So for lower link ranges, we can see the Q factor is very high in case of multiplex modes. So our system design is working very good for short range application, which are basically last mile applications. This is a tabular representation. We can see here for LG00 mode, the Q factor is very high as compared to no spatial mode transmission. So we have proposed a hybrid PON access system based on MDM for last mile application. LG00 mode is performing exceptionally well as compared to other modes, and the maximum achievable link distance in case of LG00 mode is around 950 meters, which is reasonably good for last mile services. So our system is performing very good for short range applications, and which are basically last mile applications. Hence, we can use this system for ensuring connectivity of last mile users. These are some of the applications of our proposed system design. It can be used for last mile connectivity, for remote connectivity, high-speed connectivity in case of difficult terrain. It can be used to serve IoT-based applications and VLC communication as well. Now, feature work, if you see, the operating wavelength is 1550 nanometer. We can down convert this to the range of 400 to 700 nanometer in order to integrate a core system design with VLC framework for ensuring last mile connectivity having high data rates. We need to choose appropriate transceivers so that we can integrate our design with the VLC framework. And from practical design point of view, it won't be of much concern. And by doing so, we can support high-speed connectivity of users via visible light communication in homes, malls, hospitals, in aircrafts, and moreover, we can also implement intelligent transport system using this framework. These are some of the references we have used. Thank you.
Thank you for your presentation, and we have time for a couple of questions if from the audience. Any question?
Yes, may I ask a question, Professor Aaron? Yeah, on the speaker.
Yes, sir. Yes, sir.
Yes, thanks. It's a very nice presentation. I'm just curious, perhaps it's just a comment, but how do you generate the modes on the side of your transmitters? You just change the cavity, or I mean, it's more a kind of a practical question.
Sir, we have multiple options. Like we are having some specialized lasers as well, which can generate these modes, or we can use some other techniques as well, like spiral phase techniques. We can use, computer generated holograms as well in order to generate these modes, so that we can transmit them over the channel.
Okay. Okay.
Yes, sir.
And the fiber, I mean, in the fiber that you use, you won't change the modes themselves. They will keep the modes as you just designed them to transmit over the fiber.
Yes, sir. Like we have used 4 modes, and the fiber generally they have losses of 0.2 dB per kilometer. So they are transmitted as such. But if we increase the range, like we have taken very practical link range of fiber length of 10 kilometer and 20 kilometer. If we go beyond that range, then the degradation of modes will occur. Okay. So that is depending on the application. Like if you extend the length of the fiber, then the modes will be degraded much more as compared to short length. So it depends on the parameter or the application as well, sir.
Okay.
Yes,
okay.
Sir.
Yeah. Thank you. Thank you.
Okay.
Thank you, sir.
Any more question?
Fabian, I think, has a question. Fabian Vinicio.
Okay.
Yes, good morning. I have a question about the attenuation, analysis of attenuation of the free space optical link.
Yes, sir. Sir, actually, we have considered the clear weather conditions. I mean, you know, the length is the free space link is totally dependent on the atmospheric channels. So we have taken very nominal. So in case, let us say the link is having very huge attenuation. In that case, the attenuation will rise. So depending on that, we can enhance the transmission power of our transmitter. Let us say the attenuation is too high. In that case, we can either use some advanced modulation like OFDM, which will be able to degrade the impact of attenuation. So in this work, we have considered little bit ideal conditions. So our main focus was on the behavior of the modes rather than finding the attenuation, sir. So we have considered 4 different modes for like near to ideal conditions having minimal losses, sir.
Thanks. Thank you.
Okay, Cesar, you have a
Yes,
question.
I have one, just one observation. I I saw, I think it was your last slides where you were talking about future work
Yes, sir.
because you're working around 1500 nanometers,
Yes, sir.
but in
Yes, sir. Yes.
VLC it's a little bit lower. So my
Yes,
question
yes,
would
sir.
be, how do you see it in the future to implement this, but with a lower wavelength?
Actually, sir, like our application based on last mile users. Like I'm sitting in my home, so if I'm having like VLC is what like we are having LEDs and they are sending us data. So through this network, we can remove the last mile access. Like I am capable of sending high data rates to the last mile users. Once we have delivered the high data rate to the end users, and there at homes, we can use the VLC transmitters, we can use the wavelength converters as well, so that we can downgrade the wavelength range from 1550 nanometer to 500 nanometer. The main focus is that at the home of a user, we should be capable of delivering high data rates, which our model is delivering now. VLC is the further framework. I mean, we can use appropriate transceivers so that we can transmit the data. Otherwise, we can, you know, transmit the data using transceivers which are having the range of 400 to 500 nanometer as well in the FSO link as well. So it depends on the hardware complexity.
Okay. So at the end, it will be a hybrid system for the.
Yes. A hybrid. Yes, sir.
Okay. So thank you.
Oh,
thank you, sir.
Okay, I have just one comment about from 1550 that regular laser wavelength to come to visible wavelength like 400 to
Yes, sir.
700 nanometer wavelength. There are
Yes, sir.
two items to be considered. One is the atmospheric effects like attenuation, which Fabian tried to mention before, I believe.
Okay, sir.
And also the atmospheric turbulence. So for the
Yes, sir.
last mile problem, the atmospheric turbulence and the attenuation, both of them can be modeled to take into account of the lower wavelength, like between 400 to 700 nanometer, from the 1550 nanometer laser communications wavelength. And the other comment I have about applications, I think this will be a very interesting applications right now because of all the COVID-19 and pandemic situations, for the medical applications, for the doctors to have all the data transferred to the patient's room or something. So I think that has a very good applications. And for the last mile problem, if for the solution for last mile problem, even if it is for the 1550 nanometer wavelength, I think that there will be tremendous applications for the ground to satellite communication. So
Sure.
a lot of opportunities. Just a concept. The concept, once the concept is proven, then I think that lots of applications are there, I can see. And thank you for your presentation. We have to move along to the next one.
Thank you, sir. Thank you very much. We'll look into your advice and we'll incorporate it in our future work. Thank you, sir.
So
Professor Aaron,
Yes.
I need to interrupt you because Professor Ismail is asking for a picture of the participant. So can we turn on your camera to take a picture of all the participants, please? So Give me a second to put the gallery. Yeah.
So,
yeah. Yeah, because we need to take a picture of the participants. If the audience can turn on your camera, we will appreciate that.
so what do you want me to take a picture?
No, I can take the picture, no worries.
Okay.
But I'm
Okay.
waiting.
Can you use your cell phone or something?
No, I mean I'm taking a screenshot. So say cheese.
Cheese.
I have pictures. Let me take another one.
What you prefer?
Yeah. So say cheese again.
Cheese again.
Cheese.
Okay.
Okay.
Thank you.
Thank you very much. All.
Thank you. So we can continue.
Okay. Can we move on to the next one? Next talk, please.
Yes, I will put the video.
Okay. I cannot see the full page.
Can you see the screen?
I cannot see the full title yet.
I'm having some problem, maybe. So
I can see the 2/3 of the page.
What can you see?
No, not yet.
Diego.
Yeah. Yeah. I will share the screen again. So.
Okay, but okay. Can you do the video, or I can see the picture,
Okay.
the title.
Now.
Can you make the smaller, the size smaller?
This. Smaller.
Yes, Diego, do that.
Yeah, put play. Can you? Other people can see.
No, I cannot see. I can see only the 2/3 of the.
Nice. Yeah, do that.
Yeah. Now I can see the full page.
Okay.
In my small window. But let me continue. The title of the next talk will be reconfigurable intelligent surfaces enabling future wireless communication. And the authors, I believe, Muhammad Shuaib Ayub will present the paper. So please go ahead.
Okay.
Hello everyone, my name is Mohammad Shoaib Ayub. I am PhD student in University of Santiago, Chile. Today I am going to present our paper Reconfigurable Intelligent Surfaces Enabling Future Wireless Communication. And the author of this paper are Mohammad Shoaib Ayub, Pablo Adasme Soto, who is my advisor, Ismail Soto, and Professor Demosteris Rodriguez. So let's begin the session. This is the outline of our presentation. In this presentation, I will tell you about the introduction of the reconfigurable intelligent surfaces, application of reconfigurable intelligent surfaces with current technologies, and conclusion and future research direction in the end. So first of all, I will go towards our first topic, which is introduction to reconfigurable intelligent surfaces. Here is the motivation. Can alternate transmission link be constructed? So it is a big question, and there is answer, which is yes or no. But there is some questions arises there. Can we construct a wireless channel which is less random? Current potential technologies adopt wireless channel which is called edge, but we don't have a control over it. How to overcome these issues? and we have a new paradigm, which is smart and reconfigurable wireless communication network. And we have another key enabler, which is called potential candidate, and it is called reconfigurable intelligent surfaces that we are going to discuss. Here we start our introduction. Reconfigurable intelligent surfaces, intelligent reflecting surfaces, software meta surfaces. These are the name of the single term, which is called RIS. We have chosen RIS because we are more convenient to it. And what is RIS? RIS controls the wireless medium by controlling scattering reflection characteristics, and we will discuss more in the Snell's law. In RIS, each object is coated with artificial intelligence surfaces made of configurable electromagnetic material, and these RIS receives a signal from the base station. You can see here, and inside a controller which controls the reflection and the reflection, and then it transmits the incoming signal intelligently towards the receiver. Here you can see. In the next slide, we can see here the RIS elements can guide the reflected radio waves. You can see here there is an incident wave which is coming onto the plane, and then it is going towards another direction, but it will go intelligently, and this mechanism works on the Snell's law. And this is called the meta surface, as we have seen in the previous slide. And you can see here the RIS is a full duplex where signals are dealt in analog. On the other hand, surface can transmit and receive waves simultaneously, and this is a meta surface is capable of modifying the direction of reflected according to the Snell's law. Here you can see instead of the block element we have used the RIS, like we have installed this one on the building. Now and there is a MIMO 2 by 2 system. Here you can see there are two antennas at the transmitter and the two antennas on the receiver, and the signal is going towards the RIS, and then it is reflecting back to the receiver, and it is all working on the mechanism of the artificial intelligence. And when the signal goes towards the RIS, the pin diode, which is work as a start working, and it gives the signal to the receiver. Then our signal move towards the receiver efficiently. And here is the element. RIS element is the perfect example of keyhole where it is used to drive the closed form approximation to the channel contribution. And you can now we will discuss about the RIS structure. RIS structure consists of the pin diode, biasing circuit, and the varactor diode. And in the varactor diode consists in the reflector unit, whereas the pin diode has two states, on and off. When the pin diode is in off condition, off state, the transmission surface allows incoming energy to pass. On the other hand, if the pin diode is in off on state, so the incident energy is reflected. On the other hand, vector diode is used to change the resonant frequency, and it changes the uh, resonant frequency within the available patches by the electronic tuning circuit. When we talk about the prospective implementation of a smart radio environment (SRE), the RIS can play a vital role in smart cities, smart homes, smart buildings, factories, hospitals, underground train stations, airplanes, airports, billboards, glasses, clothing, smart cars, and smart trains. These are the prospective implementation of smart radio environment under the umbrella of reconfigurable intelligent surfaces. Now move towards the second outline, the application of reconfigurable intelligent surfaces with current technologies. Here are the three most important topic we are going to discuss, which is RIS aided millimeter wave massive MIMO system, RIS aided UAV unnamed aerial vehicle system, and RIS aided visible light communication system. Let's move towards our next topic. This is our RIS aided millimeter wave massive MIMO system. This is the smart approach to manage the throughput. And it is the overview of the MIMO system, how MIMO system works. MIMO is the wireless technology that use multiple antennas at the transmitter as well as on the receiver. MIMO-based system offer improved coverage benefits unlike conventional wireless communication system. Here you can see in the 4G, but in the 5G the coverage enhancement due to the massive MIMO system is too much. So MIMO system use multiple receivers, multiple antennas. Channel can process multiple signals simultaneously. And due to its nature, MIMO is being adopted more and more with the development of IoTs, 5G and 5G beyond. It is more implementing in these conditions 5G beyond and in the future wireless communication. And here you can see if you are talking about the two antennas, if you add more antennas, so it will create a more beam. As you increase the antennas, so it narrowing the beam, focusing the energy certain direction on the pre-coding and the beam forming direction. Here you can see the 180 degree to 0 to 180 degree. So there are the multiple array elements. Here you can main loop, as you can see here, the main loop, and it has a side loop also. If you increase more antennas, so it will create a side loop with the main loop. And these are the RIS is a key enabler for massive MIMO or ultra massive MIMO system. Here you can see the RIS. Here is the base station and the base station to the RIS link, base station to the user equipment direct link, and here is the RIS to the user equipment. And what is the main implementation? Let's see. RIS enabled solutions intelligent adopt network to change in the environment, which provides the coverage enhancement and better throughput, increase the reliability, and provide the massive connectivity, which is the main function of the 5G beyond and the 6G. And it has a better to produce the signal to the noise ratio, SNR ratio, and it has the capability to provide unprecedented gain, and also it provides the high quality channel link to overcome the unfavorable propagation condition in the different environment. Let's move towards our another topic, which is RIS aided unnamed aerial vehicle. It is more important nowadays because it provides a 360-degree coverage. Let's move towards our this topic, RIS aided unnamed aerial vehicle system. It has 360-degree panoramic omnidirectional reflection, but in terrestrial it is almost 180 degree. If you we are discussing the panoramic condition as well as the terrestrial condition. In the terrestrial condition, it will work on only the 180 degree, but if you're talking about the unnamed aerial vehicle, not a terrestrial network, so it will enhance the coverage towards the 360 degree. Signal reflection serves because of the line of sight condition, because if you are using the unnamed aerial vehicle UAV, so there is no blockage, there is no line of sight condition. Signal reach towards the RIS and then goes towards the UAV, as you can see, and then it will reflect back to the user equipment. So flexible and easy to deploy because it's like a drone, and it enhances the coverage to the specific direction. RIS aided UAV enabling intelligent reflection from the sky. Let's move towards our another important topic, which is RIS aided visible light communication, the other way to exploit the spectrum. Okay, let's move towards this topic. RIS aided VLC system. RIS assisted VLC system provides zero RF interference signal. It provides the signal security, improves the transmission range as well as the signal detection. RIS improves the light reception in VLC by replacing the traditional lamps. Or RIS in VLC has a strong capability to improve the signal detection, noise, and interference. And RIS with VLC can serve physical area security PLC by secured precoding and large security capacity, and it can serve thousands of devices simultaneously VLC system with RIS. Here you can see the diagram. towards the another outline, which is our conclusion and the future direction. Here is the future direction. RIS deployment in multi-cell network. RIS practical channel estimation. RIS provides short-range and high-resolution images. RIS with Wi-Fi. RIS channel modeling. RIS reflection optimization. RIS performance analysis. RIS, RIS design, prototype conditions. These are the future directions of the RIS. And here is a small conclusion. In this research article, we have explored and briefly discussed the opportunities that are brought by CC for RIS and RIS potential candidate to get smart and recognizable environment, as well as there are the few challenges, and these are the main challenges, which are RIS reflection, challenge estimation, hardware design, power loss, and RIS deployment. And I would like to thank you for the attention and to listen to me carefully. So I'm very thankful for all of you to listen my presentation. Thank you very much.
Thank you for the presentation. We are now open for any questions. Any question from the audience? Okay, Diego has a question.
Yes, I have a question. Very interesting topic, the RIC and this kind of the reflection. But I have have you seen in your review if there is any tools to simulate this kind of surface reflection? Because usually in the lab, the guys simulate everything like noise signal and that kind of thing. And I was thinking that if we can implement that kind of new feature like the reflection to this new simulation, or if we will need something more complex. I was thinking of a friend who simulates material simulation in chemical computing approaches.
Yes, dear Professor, because it's an exciting technology and there are plenty of open problems and also no consensus on what the key uses cases will be. And there are many ideas as you have given to me about the simulation, but few convincing comparison with current technologies. In fact, even the path loss modeling, I personally feel that it is a hot topic for the future times.
Okay, thank you.
I have just one comment. Actually, I don't see that there is any hardware design or any materials available today. But I can tell you that some of the nonlinear polymer materials, photonic polymer materials, nonlinear materials, they perhaps can be used to make these IRS devices in future. That's just my comment.
Yes, Professor. Definitely, I will follow the instruction as you have given to me.
Any other questions from the audience? If not, then there is one from Caesar.
Yes. Thanks for the presentation. I just have one comment observation for the presenter. I have been working on this topic a little bit, but with millimeter waves, which is a little bit around 26, 28 gigahertz. So one of the very complex things that we have encountered at the moment is dealing with the channel, specifically channel estimation, which is a very complex topic. We want to do it in real time. So what are your appreciations on this topic, specifically channel estimation for this type of technologies?
Yes, dear Professor. As you can see here, that wireless technology that can handle the many terabits per second, and the wireless operation will then require terahertz communication. And I personally feel that the points that I made above apply to the wireless communication at the edge between devices and access points, and definitely will not to the backhaul infrastructure. And in the future, definitely I will count the channel estimation problem in my research paper, and I will try to focus first of all channel modeling and the channel estimation.
Okay, thank you. We move on now to the next one. Next. The title of the next talk is Performance Evaluation of a Line of Sight Visible Light Communication Link using an Optical Concentrator and a Plano-Convex Lens. And I believe the talk will be given by David Esteban Farfan. So please go ahead with your
Morning,
talk.
I'm David. Today, I'm going to talk about our work called Performance Evaluation of a Lost Visible Light Communication Link using an optical concentrator and a plano-convex lens. Our research group is part of the graduate program in Electrical and Computer Engineering to Federal University of Technology, Paraná. I will talk about the following. Visible light communication refers to techniques that use the wavelengths in the range from 318 to 718 nanometers to transmit data. VLC employing optical source, mainly line emitting diodes, to transmit data. The information is transmitted through free space in a line of sight or no line of sight link. Signal is received on the other end by photodetectors, typically photodiodes. VLC can serve as a complement to RF-based networks in indoor environments, where the existing LED lighting infrastructure is available and can be used to implement the data transmission. Our motivation was there are important questions to be addressed related to the performance of the VLC link centered on the photodiode and its active area, which being so small limits the angle of reception. As a solution, the use of lens has been proposed. In this work, we analyze the performance of a line of sight VLC link in an indoor environment, investigating the use of a commercial LED luminaire of the transmitter side, to which an optical concentrator was coupled, and a photodiode on the receiver side, to which a plano-convex lens was attached. The VLC system is constituted by transmitter, wireless channel, and receiver. The VLC wireless system as presented in the next figure. Consists of an input signal that represents the data to be transmitted in form of bytes. This information is modulated and sent to the current driver circuit that powers the LED. In addition to providing lighting, the LED transmits information to propagate over the free space. The optical signal is received by the photodiode that converts the light signal into electric current. The signal is then processed by amplification circuit. The modulated and the transmit bytes are recovered and the output. This figure shows the basic geometry of the VLC propagation model for an indoor environment with line of sight between the transmitter and the receiver. For indoor application, LEDs are the best choice to meet the VLC advantage of illuminating and transmitting data. LED is a transducer element that is a device that transforms one form of input energy, electrical, into another form of output energy, luminous. They present a Lambertian distribution, therefore the radiant intensity is described by this equation. The photodiode is a transducer whose output is an electrical current which is proportional to the incident power by means of the responsivity. This parameter depends on the wavelength of the incident radiation and is higher at longer than at a shorter wavelength. The received optical power also depends on the effective area of the photodiode. In this way, to improve the efficiency of capturing light and the photodetector response, an optical lens can be placed in front of it. For a loss link, the received optical power is expressed by this equation. For the transmitter, a bias chip was used in the transmitter side, which is a three-port network whose function is to couple an AC signal with the DC signal. One of the ports is used to connect the data signal. The second port is used for the power supply with DC voltage, and the third port gives the coupled data signal and DC voltage output, enabling the LED to modulate and transmit the data signal. The luminary used in the experiment consists of a round-base module composed of 7 high-power LEDs. The luminary emits white light and has a peak wavelength of 518 nanometers. In addition, an optical concentrator is mounted on the PCB in front of the LEDs. The concentrator limits the divergence of the luminary emission and concentrates the beam mostly into the line of sight direction. Therefore, this improves the amount of optical power reaching the photodiode area. This figure shows the luminary of the left and the luminary coupled with the optical concentrator of the right. The concentrator is a piece made of polymeric material which is composed of concentrator elements that are aligned with the LEDs on the PCB. On the receiver side, the Hamamatsu module was used. The module is composed of a high-sensitive EPD photodiode with a detection area of 7.1 square millimeters. The module was mounted in front of the photodiode is a plano convex lens with anti-reflection coating for the range of 315 to 700 nanometers. The photodiode transfers the received optical energy into a photocurrent, which is then converted into voltage for the signal processing and recovery. The lens is optimally positioned to focus the received light beam on the photodiode effective area. This figure shows on the left the used plano convex lens. On the right shows the lens aligned with the optical receiver. For the VLC line configuration, the transmitter segment bias T plus LED luminary plus concentrator and the receive segment receive module plus plano convex lens were mounted and aligned in an optical batch. In addition, an OOK NRC code was generated in MATLAB and loaded into an arbitrary waveform generator. For the experimental analysis, tests were conducted in an indoor environment using the line-on-sight configuration. Measurements of optical power were taken between the luminary fixed structure and optical power meter handheld instrument. Measurements were taken at every 50 centimeters up to a distance of 2 meters, without signal modulation. The electric current driver was configured for delivering a power of 3 watts. Based on the optical power measured at each point, the optical power at the optical receiver was estimated. This figure shows the behavior of the measurement optical power by the photodiode over the distance. 3 scenarios were considered. Scenario A: the power is measured when the LED luminary does not have the concentrator and the receiver module does not have the plano convex lens attached at its entrance. This is considered the base scenario, and this is the yellow line. the scenario B, the power is measured when the LED luminaire has the concentrator mounted on this front, but the receiver module does not have the plano compass lens attached. This is the red line. And the blue line, the scenario C, the power is measured when the LED luminary has the concentrator and the receiver module has the plano compass lens. We observe that the best result concerning the received power is obtained when both the concentrator and the plano compass lens are used in the arrangement, as this improves the directionality of the light beam along the loads and increase the optical power reaching the photodetector's area. Based on the results shown in the last figure, a data signal with OOK-NRC modulation was implemented in MATLAB and the frequency was set at 1 MHz in order to analyze the signal gain in each of the above scenarios. The distance was fixed in 2 meters. This figure shows the signal gain which corroborates the results of measured optical power shown in the last figure. We observe that the voltage signal response present the best performance when the concentrator and the lens are present in the arrangement. This is the blue curve. The table shows the peak-to-peak voltage of the signal for each scenario and the obtained gains with respect to the base scenario. For the analysis, the maximum bit rate that meets the condition of a very less than or equal to 10 at less 3 was evaluated. This value was taken as a reference since it is used in multiple VLC investigations to measure the performance of the data transmission. This figure shows the Baird versus bit data rate curves, where the horizontal dashed line represents the Baird level at 10 at less 3. We see that the configuration with the concentrator and the plano compass lens present the best performance in relation to the other cases. And the table shows the achievement with rate of each configuration. Well, as conclusions, we have results show that using an optical concentrator and a plano compass lens significantly improve the performance of the PLC link by optimizing the direction of the incident light and by focus it on the effective area of the photodetector. For an indoor scenario with a distance of 2 meters, a voltage gain 9.23 times higher was obtained when the plano compass lens and the concentrator were used, compared to the case in which these components are absent. In relation to the data rate, a significant improvement in the transmission rate was also observed. A data rate of 40 megabits per second was reached compared to the 16 megabits per second obtained when the optical elements are not present in the arrangement. Finally, thanks for your attention.
Thank you for the nice talk. We have time for a couple of questions. Any question or any comment? I just have one comment. Did you use software program like Zmax to do the design, optical design?
No.
David?
What happened to my comment?
I'm not sure if he has answered the question.
Did you use a ZMAX or that kind of optical software program to design the lens?
May I comment on his place? Indeed, now it is an off-the-shelf lens that we used. We bought it from Thor Labs, for instance. But concerning the luminary, used a software called Apex to design the concentrator. So, but it was in another work. It was not linked to the work of David. Okay.
Okay, Fabian.
I have another question. Thank you very much for the presentation. So I saw with the distance, the results are better when you use this combination plano-convex lens. But what happened with the field of view of the receiver? It decreases the field of view, increases the field of view.
David, could you answer this or?
Yeah, apparently. Yeah. He has problem with the connection.
Okay, so let me answer this also. Indeed, when you use a concentrator, of course, you reduce the field of view, okay? And that what makes it effective to have more light going into the area of the photodetector. So in our experiment, we try to use, for instance, the concentration on one side without having the lens on the other side, on the side of the photodiode. And then you take a look on the results, you'll see that there is an improvement concerning the signal-to-noise ratio and also the performance. And when you have both, the concentrator and the lens, it will improve much more, this performance. The question is this, you cannot, one thing that we are also concerned in our research is to have also light to illuminate the environment. And when you try to reduce and use it only to communication, the ambient, the environment light is just reduced. So you have to find out a balance so that you have a good illumination and also good communication performance in your link. Okay.
Thank you very much. Yeah, I was thinking to use, for example, this approach in angular diversity receivers. So you can have a smaller field of view, but if you increase the signal-to-noise ratio, would be very useful.
It's interesting because I think you could also use concerning these past presentations that we have seen concerning the reconfigurable intelligent surface. You could perhaps devise a component in which you can also change the field of view in order to improve also the performance and the transmission to the receivers. I think.
Thank you very much. Again.
Okay, thank you. Any other question? Is that you already asked the question? Okay, so we move on to the last talk for this session.
Thank you.
Which is text analytics architecture in IoT systems.
Hello, my name is Diego Fuentealba and I will present our work named Text Analytics Architecture in IoT System. Today we will see the introduction, the background information, system proposition, methodology, results, and conclusion. The Chilean mining industry is migrating its operation to underground mine, which implies several challenges, such as the support of ecosystem and the identification of potential problems in underground mines. For this reason, is needed automation of environment, which involves the distribution of tasks in several IoT devices to decrease the complexity. Actually, guidelines for automating tasks suggest agent systems to integrate multiple industry-level processes. And IoT devices can supervise these text flows to identify potential problems in advance. However, there is no clear evidence in the literature that suggests the feasibility of text analytics algorithms running on IoT devices with multiple agent system architecture to meet the guidelines and previous designs. The literature review includes two main topics. The first, agent system in IoT. We found that several of IoT systems using agents work on ontologies and middleware to integrate several platforms. However, they have high processing time. For that reason, multiple agent systems usually work with service-oriented architecture to provide flexibility and to split tasks. On the other hand, hybrid communication system for IoT usually work with RF and visible light communication system. However, they have a low integration and they usually have a high energy consumption. But new hybrid system resolves this problem of low integration with the interoperability through a protocol in an abstract layer. Our proposition is to provide two agents or two main agent tasks. First, a local agent for communication, which selects or analyzes channel by context, apps, and abstract protocols, which can decide according to the context which protocol is better or not for the communication. However, this work is focused on local agent system for text analytics. Previous experience showed that text analytics algorithms are very complex, so it's very difficult to process several tasks on real time. For that reason, our position includes the division of tasks to several agents. To crawler text, for instance, to pre-process text, and then to perform some complex tasks like clustering or classification. The methodology is based on design science research, where the first step is the artifact proposition, which in this case is the agent's architecture and task model as artifacts. The artifacts development, which in this case is prototype and a tested framework. And finally, the artifacts evaluation. This work fixes the technical. This work is a technical risk project, and it needs to be efficient in assessment. For that reason, the evaluation of this kind of work or frameworks is through several repetitions. And this first repetition, or the first step, is to develop a proof of concept through computational performances like indices for memory RAM and CPU. And also, we will use a text mining Vaseline algorithm like DEF and IDF, Camin, and preprocessing, which involve the remotion, stop word, and so on. This work additionally use text from strategies, mining strategies, to simulate a conversation between workers about goals in a mining context. We processes 197 messages. The architecture, the proposed architecture in this case was the several Raspberry Pi simulated with virtual machines. One of them used the PAVE framework to run several agents. And also, we use several devices to process or to run text mining algorithm for data cleaning, clustering. So the results were actually very good in the context that Raspberry Pi were able to process 187 texts, but the percentage of CPU use was 68, and the memory RAM was 254. However, the virtual machine which was running the agents needed a very low memory RAM. Actually, we didn't find too many difference between one or two agents working at the same time. And also, the CPU percentage is very low. So one Raspberry Pi can run several agents. On the other hand, the text analysis results were compared with a laptop, which actually was very fast. My laptop is very powerful. Is Intel, but however the algorithm in the laptop were not running with several cores this algorithm to compare with Raspberry Pi. We can see that the time in the Raspberry Pi was very high in comparison with the laptop. And also we found that the inertia of the algorithm, the clustering algorithm, was very different between Raspberry Pi and laptop, which can be explained because of the random seed of the clusters. So the conclusion is that we met the prototype. We met the result of the prototype with this architecture, because Raspberry Pi can run analytics algorithm, text analytics algorithm, using around 68% of percentage of CPU, 254 of megabyte RAM, and about 3 seconds to cluster 197 messages. These results are very helpful, and in the case that we can use Raspberry Pi to process analytic tests, but we will need to divide the process to several IoT devices, and multiple agent systems can coordinate these tasks to perform a complex process, such as text clustering to identify common pattern in a conversation. The main idea is to supervise several workers in an underground mine. For that reason, we can find patterns like problems beforehand. So this research creates new knowledge and future line in which text analytics in IoT can improve communication with Raspberry Pi, which will help to enhance agent management control by creating and automating new KPIs that help in more effective decision making. Thank you.
Thank you for the presentation. We have time for a few questions. If any question.
Question, please.
Okay. Okay.
Yeah, thank you for the presentation. Is in a mining environment, especially if you are going to use this for the purpose of the people on the ground, the workforce, what are the typical information you want to exchange between them or collect from them in terms of content wise? In other words, if you know what the information content is, then you can define the required capacity or the data rate per information, and therefore you can guess a typical data rate that required in a mining environment for this specific application that is the n number of bits, and then use that as a platform in order to say, well, what is your average throughput, and therefore what sort of bandwidth do I need, and can Raspberry Pi deliver this information within the given space of time and resources? Did you look at the problem from that angle, or?
Thank you for your question, Professor Fari. Well, actually, that was one of the initial concerns about this research, because we firstly make a prototype to test the feasibility to run text mining algorithm in Raspberry Pi, because our first initial aim was to supervise people, like sending message to a central unit. So in the mining environment, we hear practical problems, that they usually have problems with the connections. So for that reason, several of the systems that they make should have some kind of local processing or local control of everything. For that reason, the initial idea was to test if it was able to run text analytics algorithm with agent system in Raspberry Pi to see if we were able to find patterns. The second concern about the data, about what kind of information they can share, was faced in this case with the clustering algorithm. The clustering algorithm trying to find patterns, because if we will know the information that we want to collect, we can make some classification model beforehand. But
why is that necessary? Why is that necessary in underground environment and classification of messages? Is it because you did the classification, so you can either identify a problem or you want to make a decision very quickly? In that environment, which is very static, in most of the time, it's very static environment, yes?
Yes.
So why is it the need for classification of information?
Because we wanted to identify potential problems beforehand. We wanted to identify, for instance, some signal message from help or that kind of problem beforehand. And so actually the following one of the future work could be to put some IoT devices listening people, actually, to translate from voice to text, and then we can run the text analytics, so we can listen the people speaking in underground mines. So we can find patterns in order to supervise and monitor the system in advance. So that is one of the first steps in that case, because then the next one is to translate the conversation of people. So that is the main idea, and that is one of the future work. So why? Because sometimes you need to supervise people in underground mines, especially in that conditions, which are very, very dangerous. So our main idea is to identify patterns or potential problems beforehand, before that happen. And even though one of the works that I participate in the past, for instance, was to mine some maintenance from technical from some machines. So when you are able to analyze and to find pattern of unstructured data, you can find some problems, even if they are not aware in the enterprise. For that reason,
the pattern, just my final comment, I'm trying to understand is that, okay, the mining is a very dangerous environment. You say that you're looking for health and safety, and therefore you're looking at the faces of the miners, and from their faces, you're going to do pattern recognition. You say, well, this miner has a problem, maybe lack of oxygen level or something. And that's why I guess that this pattern recognition becomes very handy because it takes you to the source of the problem.
Yeah.
You might be sampling the weather, the quality of air, but you want to know that what is it there? Is it a methane gas? Is it something else? Because you can do that classification, gives you that power to detect things early, so you can alert the workforce to pull out or something like this. Yes.
Yes, and actually,
is that the intention?
Thank you for that comment. Actually, the thing is that we already can now, because this algorithm have one part which is based on text analytics algorithm, like the split of the division of words, the division of phrases, and that's very complex in terms of computation time. But the algorithm like clustering or classification can be used to with this complex data in another kind of data, like sensors data, like oxygen, the same data that you said. So if this work, if these algorithms are running for text analytics, they surely will work for sensors or for that kind of data. The feasibility to show that agent system can work and can deal with several text mining, because it's not just text analytics, text mining algorithm at the same time, and they can split the task. It's actually very useful, not only for text analytics, it's very useful for signal processing and that kind of things.
Okay, thank you.
Okay, now Ismail, your question.
Yes, and it's not a question. It just try to complement and recommend that Professor Farid did. Actually, it seems that the underground mine, is very stable, and the coefficient of the linear system that we try to program are very stable. This is in a way to where the action is happening. Most of the operations in mining are very difficult to model. They are very variable coefficient, changing a lot because of dust, because of sometimes a machine that remove the optical fiber, and to predict that and to analyze that using very small machinery like a Raspberry or anything else attached to the body or the people or to the helmet or in intelligent walls. Yes, it's a big challenge, and you see, it seemed to me that the use of 6G in the way that we saw today by the early presentation could be the final solution, or become to be one of the solutions to all the complexity that we find in the front of the production, in the front of the explosion. Yes, so the variable coefficient of the system are very fast, the variation of the coefficient. So thank you, Farid, for your comment. That's it. Thank you.
Okay, thank you. Any other question for this session? Well, this is the end of this session for day one. And I wanted to thank all the presenters for their lovely presentations. I think we learned quite a lot. At least I did learn many things I didn't know. So I hope it's useful for everybody, and to think about some innovative ideas for design and to make some practical applications in future. So with this, did you want to say something, Ismail?
Yes,
your hand is raised.
Yes, because I would like to suggest,
okay,
for today, that after you finish course room, that a Professor Farid close the first day of our colloquium. Yes, please. Yes, after you finish, of course, room. Yes.
So anyway, it was nice to serve you to arrange a conference for this session in my session, and thank you everybody. And so Ismail, now you can talk.
Yes, yes, yes. Just to give the possibility that Fari close this first day of our colloquium. So I will let offer to you, Fari, the final word.
Well, all right, okay. Thank you. I mean, doesn't matter. I mean, I'm so lovely to see my colleague Aaron, Professor Majumdar, and we have been working together, but we have never faced each other. This is the first time we're actually seeing each other online. Yes. And it is nice to see our senior colleagues and who have done a huge amount of work in FSO and optical wireless communication and wireless in general. I think I only missed, I think maybe an hour or so, because we had another European meeting that me and Stan and others had to go there, and then we came back and so on. But overall, I think the standard of the event compared to previous years is already, you have raised the bar quite considerably. And you had a very good attendance. At one point, you had almost 40 people from across the globe, from basically at least 4 continents anyway. And that is a good sign. And it just shows that the event is recognized and people are willing to participate, which is a nice thing. And the quality of papers and presentations are also it's very good, and it's improving, and I'm sure that it will improve. So it's nice that to see colleagues participating and so on, and I just urge my younger colleagues, researchers, that these are the future driver of the research for the next 20 odd years, to participate in discussion. Don't be shy. It's not about whether the question is relevant, non-relevant. It doesn't matter. Ask the question. Not necessarily question, make comments, not necessarily comments, suggest something, just getting engaged in that, because those are the little things that we need in order to go back to our laboratory after the event and say, well, that was very interesting comments, whether we should look into it, and if not, that time will tell. So do that. And I hope that tomorrow we will have more participants. And if you already know colleagues that they are interested in this area, invite them. I already invited a huge number from Europe, which they did. I saw a number of faces, names there. So please, the event is also live on YouTube, and please advertise it. The more people we have, the better it is, because the science can spread across much wider people and different skills and ages and so on and so on. So I just wanted to thank you guys for this, and we look forward for tomorrow morning. Is it at the same time at 10 UK time, which is 11 European time?
Yes.
Almost.
Yeah. Well, yeah. Good. Well, just like to say thank you for the chairs, because they're sitting there patiently, yes, listening to all the speakers and so on, and making sure that things, the program flows nicely. I'm very grateful for them, and I really appreciate what they have done today. Special thanks to all of them.
Thank you.
So go and have your lunch or evening, whatever it is. Yes, lunch.
Yes, lunch.
So yeah, here it is almost coffee break. So I'm going to go for my coffee, and I guess in some part of the world it's almost dinner. So we will see you tomorrow morning at 10 UK time.
Yeah. Thank you.
Take care, guys.
Okay. Thank you. Thank you, my friend.
Thank you. See you
Bye
tomorrow.
bye.
Thank you. Bye bye.